Hey, hi, hello. Am I audible?
Yes, sir.
Okay. So, is there any noise from my side, or is it clear?
It's fine, sir.
Okay. Just 1 minute, and then we start. Okay. So, quiz 1 week the revision. First week I'll be doing it. Week 2 Nitin will continue. Week 3 Anamika will do, and then I'll be back for week 4. Okay. So that's the sequence in which we'll go.
Excuse me, sir.
Yeah.
Sir, before starting this session, can you please tell my doubt? I have one small doubt in GRPA 2, question number 3.
GRPA 2. Which one? Which course is this?
Sir, in MLT GRPA question number 3. GRPA 2, question number 3.
There are no GRPAs, right? In
Oh,
ML.
sorry, graded assignments. Sorry.
Okay, yeah. Okay. Which week? Which?
Sir, second week.
Okay, so we'll discuss that when we do, the week 2. So Nitin will, go over the revision part, and then that will be addressed. Okay, because we
Sir,
are going.
I'm not going to take the whole live session.
Agreed, but we have a certain plan moving forward, right? So we would like to start from week 1 and go in that sequence, right? So that we'll certainly address it, but when we do week 2, we'll surely address it.
So, sir, please discuss, sir, question number 3 from graded assignment 2.
Yeah, sure. Yeah, we'll do that.
Okay, sir. Okay, sir. Thank you.
Sir, are you live streaming this session?
See, streaming is not working, but Nitin is recording it, and we will upload it right away after the session ends.
Okay, that will work. Thank you.
Okay, so we start then. Most of this you would have already seen. So first 4 weeks is going to be unsupervised learning. So we have this the syllabus. So representation learning, we have PCA, kernel PCA, and we have clustering, and then estimation, where we mainly look at MLE, Bayesian estimation, and EM algorithm for Gaussian mixture models. Okay, so basic theme for all 4 weeks will be compression leading to comprehension, as the professor has mentioned multiple times. So we are basically trying to compress the data set that we have in some way, and by means of that compression somehow try to understand or comprehend what the data is all about. So the first 2 weeks we deal with what is called as representation learning. So given a set of n data points, how can I learn some kind of representation of these data points, so that by this alternate representation I achieve some kind of compression and thereby get a better understanding of the data. Okay, so representations and reconstructions, we'll use these two terms interchangeably. Okay, so that is something you need to be aware of. Okay, so what is one way to measure if we have a good representation or not? We use what's called the reconstruction error, right? So given a data point xi, I am reconstructing it and calling that reconstructed data point xi superscript r. Okay, how close are these two data points? For that I use the Euclidean distance, right, or the L2 norm. And since the L2 norm has a square root associated with it, it's always easier if we have squared distances, right? So we square the distance and then sum it across all n data points and divide by n, right? So this is in some sense the average error. That's what we mean by the reconstruction error here. So the smaller the reconstruction error, better our representation, right? So this is all things you should already know. So what is a good representation? The one which minimizes the reconstruction error. And so the obvious way to minimize this would be to set the reconstruction as the original data point itself, right? So if I say that the reconstructed data point is equal to xi, then the left hand side will become 0. Okay, so but is that a good representation? That is not, right? because why is that not a good representation? Because we are not really learning anything in the process. So our goal for a good representation is twofold. One is to minimize the reconstruction error or to have a small reconstruction error, but that alone is not sufficient. We also need a large compression ratio, right? So we need to make sure that in the process of reconstructing these data points, we also achieve some kind of compression, right? So that is our goal. So the main theme, or rather the main sub-theme I would say is looking at proxies for these original data points, right? So a proxy is nothing but some other representative for a given point. So if you consider, say, a data point like this, which is given in blue, now one potential proxy could be this green point here. Another proxy could be this green point here. So which one do we choose? So we choose the one which has a smaller error, right? So this is in some sense a measure of how much error there is in reconstruction. And in this case, this green point would be a better proxy for this blue point. Now, in general, what is the best proxy? Best proxy would be
orthogonal one.
the orthogonal one, right? So the one which the error, yeah, that's the error being perpendicular to the chosen line. So that would be the best proxy. Yeah, the YouTube link is not working. We are recording the session. We'll upload it. Okay, so that's the best proxy, and this image will be very useful for you. So please commit this to memory. Okay, so given a line, every line is represented by some unique W vector, right? So this is nothing but a unit circle, and W is one point on this unit circle, right? This is the line we have chosen. X transpose W is the scalar projection of the point X on the line W, okay? And the vector projection will be X transpose W into W. Okay, so there are two projections. I hope you're all aware of this, just a terminology, but still. One is the scalar projection, which only gives you the scalar value, which is X transpose W. The other one is the vector projection, which is that scalar times the vector. Okay, so the error is nothing but the original data point minus the projection. Okay, so that will be your error, which is given by this. So far, are you all paying attention? Any questions so far? Okay, so now the goal is to, as we have already seen, minimize the reconstruction error. So even before that, one important point is these formulas work only if W is unit norm. Okay, so if you are given a vector that does not have unit norm, then you have to convert it into a vector with norm equal to 1 and then apply this formula. Okay, so please don't
Excuse me,
forget
sir.
that. Yeah.
Sir, can you please repeat the part about scalar and vector projections?
So this X, the projection of X on W, so typically when we say projection, it could mean either of these two, right? So there is a scalar part to it.
Yeah, the
So
dot
let's
product.
the dot product, right? So the dot product is just the scalar part, right? So that's the scalar projection of X on W. And let's say the dot product comes out to be 3, then this is like 3 times W. So the 3 is the scalar part, and 3W, the whole thing we call it the vector projection. I mean, just terminology.
Okay, got it. Thanks.
Okay, so yeah, so remember that this is true only if norm W equal to 1, and then what we have here is the error for the best proxy, right? So this is the smallest error that you can obtain, right? So that is that. So now for a full data set, this is nothing but sum of errors for all the endpoints, and then you divide by n. So that is the reconstruction error for a data set. And once you are clear about this, what we need to do is we have to minimize the reconstruction error. Okay, so we look for that direction W such that the reconstruction error is minimized. Okay, so a bit of algebra will convince you that this objective on the left hand side can be rewritten as this one on the right hand side. So minimization gets converted to maximization, right? So what you have on the left is minimizing the reconstruction error. What you have on the right is maximizing variance. Okay, so this is nothing but the variance of the data set along the direction W. Okay, so it's a very important point. This is these two, the equivalence of these two is something that you should know. So we typically end up working with the maximization problem, and again, a bit of algebra will convince you that this can be written in this form. So what is this thing inside the bracket?
Covariance matrix.
Okay, so that is the covariance matrix. In what? So is it always the covariance matrix, or are there some conditions for it to be called the covariance matrix?
When this W is equal to unit norm, then only it becomes a covariance matrix.
No, right. So see, W, the covariance matrix doesn't have anything to do with W, right? So this thing inside the bracket is,
Oh,
When
this
the data points are
when it's
centered.
okay, yeah. So that's an important point, right? So this is true only if the data points are centered. Okay, so otherwise the general formula of the covariance matrix is will have one xi minus mu into xi minus mu transpose, right? So because that mu equal to 0, we can call it the covariance matrix, right? So just one quick word on centering. I'll just go back and refer to this diagram here. See, one assumption that we have for PCA is that the whole setup is linear in some sense, right? So we assume that the data set lies in some low dimensional subspace of RD, right? So all your data points are in RD, and you assume that your data set lies in some lower dimensional subspace of RD. So the moment I say subspace, we are talking about vector spaces, right? So, and the moment we talk about vector spaces, the origin is very important, right? So the vector spaces, so all vectors in some sense, what do? They have their one end at the origin and another end pointing somewhere else, right? So if the data set is not centered, then your important directions will kind of be influenced by where the data set lies, right? By centering, you're removing that difficulty, right? So centering is very important. So one quick point, what are the, so when we say subspaces, right, what could be the subspaces for, say, something like R3?
R2,
Sorry?
R2.
Okay, is there any other better way of saying that?
Origin, X3, x-axis, y-axis, any two-dimensional plane.
Okay,
All
right.
are subspace.
Okay, so see, why I'm saying this is because when you say that the assumption is that the points belong to some subspace, what we mean is, for the simple example of R3, the points either lie on a line passing through the origin or a plane passing through the origin, right? So this through the origin is important. If they don't pass through the origin, then they are not subspaces. Okay, so which is why centering is a must. Okay, we'll move on. I have
Sir, why is this origin condition important?
the origin is important because of the theory of vector spaces, right? So a vector space is so a subspace, right? Is when can you say that a set is a subspace of a vector space? Only if it has the origin in it.
Origin. Okay. Yeah, I got it.
Okay, so yeah, so that is the covariance matrix. So we come back to the maximization problem. So when will this be maximized? What is the solution to this problem? What direction will maximize this W transpose CW?
The largest eigenvalue of covariance matrix.
Right. So what will be the direction? So if you look at argmax of W transpose CW, what will it be? So if I ask you this question, that what is the argmax of W transpose CW, what will be the output of that?
W star.
What is W star?
Eigenvector.
The maximum the W for which the quantity is maximized.
Okay. And what is that W?
Eigenvector corresponding to maximum eigenvalue.
Okay, that's right. Okay, so the argmax of this is the eigenvector corresponding to the largest eigenvalue of the covariance matrix. Okay, so that is the argmax. What will be the maximum value of this expression? Argmax you know now. What will be the maximum value?
The eigenvalue.
Okay, the corresponding eigenvalue, right? So lambda 1 will be the maximum value of this expression, and the argmax will be W1, which is the eigenvector corresponding to lambda 1. Okay, I hope all of you are clear about this. This is like the most important part of week 1, right? So what is the maximization problem? How do we arrive at it? So this is something you must know. Once you are clear about that, we next move on to directions, right? So there are multiple directions. So far we have only looked at what is that one direction which minimizes the reconstruction error or maximizes the variance. But it turns out that there could be multiple directions in your data set. So for example, this looks like some sine curve that is rotated by some 45 degrees, right? So in this case, this is the most important direction, that is quite clear, but we can't just throw away the information present in the other direction, right? In this case, say orthogonal to this line. So we move from the error vector to a better name for it. We call them residues. Okay, so xi transpose W is the projection. Now, after you project it, what remains is now called the residue. So what we do is we continue doing this process of finding the best line. Now, instead of the original data points, we do it for the residues. Okay, so that's the second round. So in the second round, what do? We look for those directions which maximize W transpose CW. Again, norm W is equal to 1. All that remains the same. But we no longer search everywhere. We search only for those directions which are perpendicular to W1. Okay, so we keep looking for orthogonal directions which maximize this expression. And what would the second direction be in the second row? What is the argmax here and what is the max?
It will be the second eigenvalue and the second eigenvector.
Okay, right. So it will be the second largest eigenvalue of the covariance matrix. That will be the maximum value, and the argmax will be W2. Okay, and in general, if you continue this process, the kth round will give you the kth eigenvector corresponding to the kth largest eigenvalue of C. Okay, so these, if you keep doing it, and eventually there will be a total of D such vectors, because there will be D eigenvalues for a D cross D matrix, right? And there will be D eigenvectors. So we can come up with this representation, right? So what is this? So Wk is the kth eigenvector and xi transpose Wk is the scalar projection on that. Now, if you sum this up for the first capital K principal components, as they are called, you will get one reconstruction, right? So this is one representation. Now, what happens if capital K equal to D? Is there any use if capital K is equal to D, the dimension of the space?
No use.
Okay, why is it not of any use?
There's no compression.
Okay, that's right. Right. So there's no compression if capital K equal to D, because so why is there no? So why is it equal actually? So what is the reason for that?
Because there is no loss of data. We are just reconstructing the original data point.
Okay, why is there no loss of, like, why is that true?
Or is it
If the data points
Yes.
lie
They may
on
be
a linear
non-linear.
so
if the I mean already the relation is like the features are independent, then K would be equal to D.
Okay, so my question is,
It is not separable in the
Sir,
linear
if K is
subspace.
equal to D, then at the end of
They are not
Kth
they are not
iteration,
belong to
the
any
respective
subspaces.
okay, that is kind of correct, but can you be more specific? So,
A k-dimensional linear subspace of Rd.
okay, but yeah, so
All
if
residues
capital,
will lie on the same line.
okay, so
If
what,
D is equal to if D is equal to 2 dimension, similarly we can, if we explode it to K, then same it becomes there.
okay, so what are, okay, I'll ask this follow-up question maybe. So what are W1, W2, so on till WD? What, that set of vectors, what are they?
The eigenvectors.
Principal components.
Okay, they are eigenvectors,
so
but
what?
Representation.
Coefficients.
They're also the basis for RD.
someone said base,
They're
right? So
orthogonal.
that's the point. So they are a basis. So what kind of basis are they?
Orthonormal.
Okay, so they are an orthonormal basis, right? So moment you say that they are an orthonormal basis, and if capital K equal to D, then the right hand side should be xi, right? You are just representing the point xi in a different basis. Okay, so if capital K equal to D, then you are just reconstructing the original point by representing it in a different basis. Okay, so that is the reason why xi are equal to xi if K equal to D, and there is no point of doing that. So you don't achieve any compression, nor do you achieve any reduction in the dimensions. Okay, so so this is the motivation for going for a smaller value of K, meaning K less than D. Okay, so before we jump to that, I hope you all know this, right? So how we come across this? So CWK is lambda K WK because WK is the eigenvector, and WK transpose WK is 1. Why is that 1?
Because it is
So
orthonormal.
orthonormal.
Right. So because it is orthonormal, right? So again, these are, I think you all know this. So now once you have the lambda case, lambda 1, lambda 2, say let's say there are 4 lambdas. Now, how do we choose K, right? So that's a big question. How do we come up with a good value of K? So one heuristic for that is choose that value of K which achieves this ratio, right? So in the denominator you have the sum of all eigenvalues. In the numerator you have the sum of the first capital K eigenvalues. So whenever that ratio exceeds or is greater than or equal to 0.95, you stop there and you say that I am going to choose the top K principal components and stick to that. Okay, so there is a different way of understanding this, which is the variance approach. Okay, so what are these n values? Think about this as
Scalar projections of the.
These are the scalar projections, right? So now, what will be the variance of this data set that you have?
1 by m summation xi transpose w whole square.
Right. The square of the. Right, so that's good. So this is the variance. Okay, so now remember that this is what we were trying to maximize earlier. So this is the variance along what? When I say variance, what do I mean? So this is
Along the principal component.
along the WK. Okay, right. So this is the variance along the K principal component. Okay, so this is, I think you all are very clear about this part. So we are trying to. So when we say PCA is variance maximization, what we mean is that we are trying to maximize the variance of the data set along a particular direction. Okay, so now this is again WK transpose CWK, which is lambda K, right? So lambda K is nothing but the variance of your data set along the K principal component. Okay, so a few more important points. So for a data set in say RD, you don't directly get hold of the variance of that data set. So if you have say 10 numbers, 10 real numbers, then you can very clearly defined variance, and there is only one such quantity. But when you're talking about, say, R3 and R4, you are not going to get simply a single number called the variance. You will get what is called the covariance matrix, right? So let's take the case of R3. You get a 3 cross 3 matrix. And what do the diagonal elements of this matrix represent?
Eigenvalues.
Eigenvector.
Sum of the
Eigenvalues.
Root of eigenvalues.
Okay, so the small correction there, they don't represent the eigenvalues, right? So see, the covariance matrix, all that we have is that the diagonal values represent the variance along the kth directions. Okay, so let's go back. We have a C somewhere. C. Okay, I don't have the matrix form here, but this is important. See, C, the diagonal elements of C are not the eigenvalues. The diagonal elements of C are the variance along the D different directions. Okay, is that part clear? Is anyone having a confusion there?
Yeah,
You
so can
don't
you repeat that please once?
Okay, so okay, see, I'll just give me 1 minute. I'll open a just open a different tab.
Excuse me, sir, but what I know is that the variances are the eigenvalues.
That is correct. That is correct. You are right. I am not disputing that. See, variances are the eigenvalues. So the variance along the kth direction is WK transpose CWK, but it's not the kth diagonal element, right? It's not CKK. That's what I'm saying. So I'll just quickly.
No, for general matrices also trace is equals to sum of the elements only, right?
That is correct. So wait one second.
Sum of the diagonal elements.
So you have a matrix C, right? So C is the covariance matrix. So what I am saying is, this is C11, this is C22, this is C33, right? So what are C11, C22, C33? Are they the eigenvalues of C? So you all done MLF that part, right? So I think everyone knows what that is now. But so are the diagonal elements the eigenvalues of C?
No, variance.
No, variance.
Okay, so C11 is what? The variance along the first direction, right? Along x-axis, yeah. So C22 will be variance along y-axis. C33 will be variance along z-axis. So there is no confusion there. What we are saying is, let me now go back. So, okay. So is that clear now? So what we are saying here is slightly different. The trace of C is what?
Lambda 1 till lambda k.
Lambda d, right? So if there are d values.
Yes, lambda.
Okay, so trace is, so what property does this trace have? Trace is the sum of eigenvalues. Is that correct?
Yes,
sir.
Yes,
Okay. So the trace gives you what? Of the covariance matrix, in some sense, gives you a measure of the total variance in the data set. Okay, so there are d directions in total. So lambda 1 is the variance along the first direction, lambda d along the d direction. Now if you add all these variances together, you get the total variance in the data set. Now I'll go back to this heuristic. Now do you understand what we are doing? So we are looking at those k directions which will explain 95% of the variance. Do you now understand this terminology of what we mean by why this heuristic was used in the first place? The denominator is a measure of how much variance there is in the data set. The numerator is how much variance there is in the first k principal components, first k directions. Okay, is that clear?
Yes, sir.
Okay, so yeah, see again, the diagonal elements of C are the variances along these directions, but they are not variances along the eigenvectors. Please make a note of that.
Please repeat, sir.
Okay, see, there are many directions involved, right? So the variance along the kth principal component is lambda k. That is given by wk transpose cwk. Okay, so this part is clear. Now what I'm saying is this is not equal to the kth diagonal element of capital C. That is all I'm saying. Is it still confusing?
Actually, not getting what you are trying to explain.
Okay, so
So basically, the values are same, but the directions are different.
exactly, yeah. So see,
Okay.
C11 is what is the variance along your x-axis, right? The normal x-axis that you have chosen. Whereas lambda 1 is what? Is the variance along the first principal component. That's a different direction.
Right.
Yes,
Okay,
yes.
that's all. I mean, I think that is where the confusion was. So these are two different directions that we are talking about. So the reason I brought this up is someone was, I think, pointing out that the lambda ones are the diagonal elements of C, which is not the case. Okay, that is true only if C is like a diagonal matrix. Okay. Anyway, so you don't need to worry about all this. The only thing you need to know is the variance along the kth direction is lambda k. Okay.
So this
Yeah.
lambda k has minimum variance, right?
So maximum variance. We are looking for directions that maximize the variance, no?
Lambda 1 will have minimum variance.
Maximum. See, lambda 1 is what? It is the variance along that principal component, that direction. So, which has, where you're essentially what? Trying to maximize the term on the left, right? This is what we started off with. Variance maximization, right? That's what we are trying to do.
So just can you 5 minutes discuss, sir, what is the similarities over here with the SVD that we did?
So yes, I'll come to that, right? I'll come to that in a while. So just 1 minute. I'll just finish this off and come there. Okay. Yeah. So if anyone's still confused about this whole diagonal thing of diagonal elements of covariance matrix and
Excuse me, sir.
yeah.
Can we say lambda 1 as the maximum of maximum among diagonal elements of C?
No. See, the diagonal elements of C do not. The only thing that they have in common with the eigenvalues is that the trace of C equal to sum of eigenvalues, right? Other than that, they don't have anything to do with the actual eigenvalues lambda 1 to lambda n. Okay, so maybe I'll come back at the end after. So I think week 1 we are running out of time. So if anyone still has problems with this part alone, right? We'll discuss it after week 4 is done. Is that okay?
Yes, sir.
Okay, so
Yes, sir.
some linear algebra aspects that you have to know. So what properties does the covariance matrix satisfy?
D into D.
Okay, D into D. What else?
Symmetric.
Okay, it is symmetric. What else?
Semi-positive.
Okay, it's positive semi-definite, right? So it is symmetric and it is positive semi-definite. So because of this, what will happen to the eigenvalues?
Greater than equal to zero.
Okay, they'll all be non-negative. Okay, so I think Samit asked for this thing, right? So the relation to SVD, I won't go into SVD, but the covariance matrix is what you call diagonalizable, right? So you can diagonalize
Yes.
the covariance matrix, and the interesting thing is you can diagonalize it using orthogonal vectors, right? So you can write the covariance matrix as W diagonal matrix W transpose, where the diagonal matrix is nothing but your eigenvalues. These are the variances along the d directions, d principal components, and W will have all the eigenvectors columns. Okay, so this is in some sense SVD, right? So it's not really SVD of the data matrix, but you are decomposing your covariance matrix into 3 different matrices. Okay, so again, I come back to this after we finish week 4. So from the exam point of view, last 2 slides, see, whenever we mention standard PCA in the exam, we mean vanilla PCA, whatever is done in week 1. If it is about kernel PCA, it will be explicitly mentioned. If not, if whenever you see standard PCA, use whatever you have learnt in week 1. Okay, so what do we mean by compression? Again, you have say n data points and they're all in RD. So n times d will be the size of the samples, right? The size of this data set. So when you're reconstructing it using the top k components, what we are doing is we are using these k principal components, right? All of them are in RD. So you have k times d values for that. And then you have to compute the projections for the endpoint. So you have k into n values. So this is the size of the reconstructed data set. Okay, so note that the reconstructed data set also lives in RD. Okay, so reconstruction is different from dimensionality reduction. So don't confuse the two. Dimensionality reduction is slightly different. So instead of reconstructing the whole data set, what you do is you only retain the top k scalar projections. Okay, so if you have a d cross n data set, then you convert it into a k times n matrix. So this is dimensionality reduction. Whereas what I showed before was you reconstruct the whole data set again. So the two are different. So does everyone get that part?
But we
What we mean
PCA
by
we call dimension reduction only, right?
See, that's dimensionality reduction is a consequence of PCA. Okay, so we use it to reduce the number of dimensions, but that is not the only perspective from which we have to look at it. Okay, so this is also important. Okay, so see, finally, both this also achieves compression. This will make more sense when we do the kernel version, right? In the kernel version, we don't have access to the W's, right? Here we have access to the W's, so I can actually come up with a complete reconstruction. Whereas if you are using kernels, you may not have access to the actual WIs. Okay, so I think week 1, that's all I had. Any questions? If not, we'll move to week 2. Yes, Prithvi.
Yeah, sir, I had a question regarding one of the aspects taught in the lecture. Um, Professor kept repeating a particular line. He keeps saying data living in a low dimensional linear subspace, and he said the residues become 0 much earlier than d rounds if you're running PCA.
Right,
So
yeah.
that aspect I did not understand. How I mean, what does he mean by living in a low dimensional linear subspace?
So what he means is, let's say your data is in R3, actual data is in R3. Okay.
Okay.
So, but it could be that the entire data set only lies in a plane in R3. So a plane passing through the origin. Visualize a plane passing through the origin, and all your data points actually are in this plane. But the plane is embedded in a space, right? In R3.
Okay.
Okay, so when you do PCA, after 2 rounds of PCA, you would have found the 2 two directions that describe that plane. Okay, so moment you describe that plane, you have described your data set that lies in that plane. So the third round will be 0. It will be pointless doing the third round.
So if all the points lie on a plane, then will uh, one of the points in those vectors, I mean the vector representation of those points, will one of those be 0 for all of them?
So if you go back to the basis representation, right? So we said that was the reconstruction part. So this representation is there, right? So Xi, so in the R3 to R2 case, Xi transpose W1 and Xi transpose W2 will make sense, but Xi transpose W3 that also will make sense, but that will be 0.
Right,
There will
right,
be no
yeah.
projection of that point on the third principal component.
Right, okay.
Okay, so that's why he says it will become 0 well before the D throw.
Right, okay, okay. So is that how we are getting the compression? Like we are getting it much before D round, so is that how we are compressing it?
Yeah, that is how we are compressing. So in real life scenarios, what will happen is it will never become 0 because your data will not actually lie in some small k dimensional space, which is why we use heuristics like this 95%.
95%. Okay, okay, got it. Thanks.
Okay.
Excuse me, sir.
Yeah. So last question, because we are like we'll address other questions after week 4. Okay. Yeah.
Sir, that you said that origin should be there for being at a subspace, but if that would be the case, then zero vector will be in the subspace. But then how it will become the basis, or it will as it will become linearly dependent if we consider zero vector in the subspace.
See, the zero vector is not a part of the basis, right? So only if, I mean, zero vector can't be there in the basis, right? That was, so why I said that was just to motivate the whole idea of centering, right? Why should we center? That is the reason we discussed that part.
Okay, sir.
Okay, anyway, so others, if you have any questions on week 1, we'll come back after week 4. Okay, so Nitin, please carry.
Yeah, okay, let's start. Am I audible properly?
Yes, sir, we can hear you.
Yes, sir.
So, good evening, everyone, and I'll continue with week 2. And it's in the continuation with week 1, where we will address some of the issues with the standard PCs. Okay, so first, let me share my screen. Give me 1 minute. Is my screen visible?
Yes, sir.
Okay, so in week 2 we consider the issues with the standard PCS, and we'll try to fix those problems with those issues. Okay, so there's two main issues with the standard PCS. One is the time complexities issue, and the second is nonlinearity between the data points or between the features. Okay, and we'll address these two issues here. So first one is time complexity issue. So what I mean by time complexity, remember, in that PC algorithm, we do the I1 decomposition of the covariance matrix, which is defined as 1 by n x transpose. So if x is a data matrix of the shape d cross d, d cross n, so x transpose become d cross d matrix. So the eigen decomposition of the covariance matrix is of order d cube. So the PCA algorithm is actually order d cube, and whenever the dimensions that number of features become very large than the number of data points, then this algorithm becomes very computationally lengthy. So that is what I mean by time complexity of the standard PCA. Now we'll see how we can come up with some different algorithm to solve these issues. Okay, so there is one different algorithm that we can solve these issues. Okay, so let's see that how we arrived at. Okay, so in this particular session,
Nitin, just sorry, can you go to the slideshow mode?
sorry, Kartik, what?
Can you present it in slideshow mode so that more space? I mean,
Yeah, it should be full screen.
yeah, full screen. Yeah.
Isn't it in full screen?
No, sir. You have to start the slideshow. If you press F5, I think it will happen.
No, here it's in the. I'm seeing on the full screen. Let me check once.
Oh, I think you've just shared your window instead of the screen. I think that's what is happening.
Okay. Let me share my video screen there. Is it fine now?
Yeah, this is good.
Okay. Okay, so before going to the algorithm, there's one fact from the linear that we can the PCS, the principal component that we got using the covariance matrix, actually can be written as the linear combinations of the data points, and this claim can easily verified by just because the notation I'm using the same as we use in the week one. WK is the eigenvector, the kth principal component, kth largest principal component. It's actually the eigenvector corresponding to the kth largest eigenvalues of the covariance matrix. Okay, so this is the eigenequations of the covariance matrix. If you do some manipulations
Excuse
here,
me, sir. Could you slow down a little? Like you're running very fast. At least to me.
okay, I'll try.
Thank you, please.
So here I'm saying that these WCs are the kth principal component. It's actually the eigenvector of the covariance matrix corresponding to the kth largest eigenvalues. So just the eigenequations I've written down here. If you do some manipulations here and there, you can see that these WCs are nothing but the linear combinations of the data point xi. Right? Just write the C as the 1 by n xi transpose for all the data points. If you do some manipulations here and there, you can verify easily this equation that WK actually can be written as the H size. And our ultimate task is to find the eigen directs, I mean the principal components. And if we can somehow can come up with these coefficients, then we are done, right? Because we have the data point with us, and if we can find out these coefficients somehow, then we have the we have the principal component with us. So how we can find these alphas, I mean these coefficients? Okay, so for that, I'm not going to the proof of that. If you want to see the proof, you can see the slides, or you can refer to the lectures videos. Okay, so this is the vector notations of that the principal component is nothing but the linear combinations of the data points. Okay, so where these alpha k's are nothing but these coefficients, right? And remember there, remember in this coefficients, wk is again there. So how you will find these alpha k's? Okay, so there's some bit of algebra involved there, but if you look at those, you can find you get this equation where it says that alpha case follows this equation where k is the x transpose x matrix. Remember, this now becomes n cross n matrix. So this alpha case, those coefficients actually follows this equations. Okay, if you look at this equation properly, it is nothing but the eigen equations, right, with the matrix k, where alpha now alpha k's become your eigenvectors corresponding to n lambda k eigenvalues, right? And
yes, sir.
the same lambda k, so yes,
could you explain what is alpha k?
So alpha k's are the coefficients. So I just explained that this is my first claim that those PC principal components are nothing but the linear combinations of the data points, right? So this claim actually can be verified, but just doing this manipulations on this eigen equations. And if you get this equations, I mean that WK is the nothing but the linear combination of the data points xi. So these coefficients are I'm calling as the alpha k. Okay.
Okay.
So alpha k is a vector here. So this there will be n such components. So this will, let's call it alpha k1 up to alpha kn. Okay. So this is a vector corresponding to wk. Okay. So this gives you the these coefficients. Okay. Yeah. So this alpha case actually follows this eigenequations, and where this lambda k is actually your the kth largest eigenvector eigenvalues of the covariance matrix K. So are we done? If we solve these equations, we can because we have K with us. If we solve this eigenequations, I mean, if I find the eigenvalues and eigenvectors, can we have alpha case with us now? Because this equation says that this alpha k is the eigenvector corresponding to the eigenvector lambda k, right? Eigenvalues and lambda k, and we can easily find out the eigenvalues and corresponding eigenvectors, and so we have alpha k with us and this corresponding eigenvalues. So are we done? We only need alpha k's, right, to get the w k's. This w k's, if we have alpha k, we have w k. But this problem doesn't solve that which one is your largest principal component, the first principal component, which one is your kth principal component, right? In the covariance matrix, you can solve those maximization problem, and using that you can say that the eigenvector corresponding to the largest eigenvalue is actually your first principal component, and similarly the kth eigenvector corresponding to the kth largest eigenvalue is your kth principal component. But here is not the case, and for showing that, we'll do some.
How are we arriving at this equation? It's written doing some algebra, we get this.
Yeah, doing just some algebra using the covariance matrix.
Understood.
Okay, so I'm not going to prove this this entire algebra there. It's just a mathematical part. You can check there on the slides. So, I mean the lecture slides.
Excuse me, sir.
Yes.
Yeah, sir. Like regarding this algebra that we are talking about, I have seen the lectures. It seems quite complicated. Do we need to worry about this from an exam standpoint or not?
In exams, you actually you really need not to write the proof or false, but you should know what actually going on behind every step and all. It's better if you get a look at those and try to understand what's actually going on.
Okay, got it.
Okay, so our problem still didn't solve because we have eigenvectors, eigenvalues, but we cannot say which eigenvector will give you the first principal component and which one will give you the kth principal component, right? So here is another fact about that will solve this problem. And one more thing, we always takes the eigenvalues of the norm one, right? Wk with the norm. We only consider the principal components. I mean the eigenvectors with the unit norm or the unit vectors, right? So using that form, we can get that if you write wk as x alpha, from there you can easily verify that this alpha k should satisfy these equations, right? Where k is the matrix x transpose x. Okay.
So K is the kernel matrix here, right? Or the
K generally kernel matrix. Kernel is actually defined for different transformations, and if you take identity transformation, then you can call it a kernel matrix corresponding to the identity
so
transformation.
in this equation, what is K?
Here K is actually x transpose x.
X transpose X. So, but X is the original data points, right?
Original data point. So if you think this as a identity transformation, then you can call it a kernel matrix.
Okay. Thank you.
Okay. Okay. So for actually finding the principal components, there's one fact as well. This fact says that the non-zero eigenvalues of xx transpose, and this is x transpose x. Non-zero eigenvalues of xx transpose and x transpose x are the same, and using some algebra, we can say that this alpha k is all nothing but beta k upon root over n lambda k, where beta k is the kth the unit eigenvector corresponding to the kth largest eigenvalues and lambda k. Remember, lambda k, I am taking the eigenvalues of the covariance matrix. So n lambda k becomes, so covariance matrix was your x transpose, and we are saying that the eigenvalues of x transpose and x transpose x are the same. So the eigenvalues of x transpose x become n lambda k, right? So so here beta, if you find out the beta k's correspond to eigenvector corresponding to the largest eigenvalues of the k matrix, and always take the unit eigenvectors there, right? Beta k is the unit eigenvector and divide it by the root over the eigenvalues, right? So this is your eigenvalues of k matrix, okay? The kth largest eigenvalues. That will give you the actual alpha k. That will correspond to your kth principal component. Okay, so from there, now we have alpha k with us, and we have alpha k. Your principal component will become the linear combination of the data points, right? That's what we need. So if you look at the entire algorithm, so, first step is you have to find that k matrix which is x transpose x. Second, you have to find that eigenvalues, and so you have to compute eigen decomposition of the k matrix. So let's say you have n lambda 1 up to n lambda k. These are in orders. All eigenvalues of the k matrix and corresponding eigenvectors are beta 1, beta 2 up to beta. These are your all unit eigenvectors. Okay. Now the third step, you have to find alpha k, and alpha k is nothing but beta k upon root over n lambda k. So it's the unit eigenvectors and the corresponding eigenvalues. Okay. Once you have alpha k, your wk's become x alpha k, and you have your principal components in another manner. Now our issues were that you have time complexity issues of order d cube, right? Now if you look at this eigen decomposition here, k matrix become n cross n, and we are saying that whenever d becomes very large, the eigen decomposition is, has lowered down to order of n cube, where d is greater than n. So to some extent we have resolved our issue of time complexity.
Sir, for step 2, the eigenvectors are always unit. Unit means they are of norm 1. Huh? Whatever beta 1, beta 2 we compute, that is all unit eigenvectors.
Unit eigenvectors, and for finding those coefficients, you have to divide it by the root over the corresponding eigenvalues. Okay. So if you have been asked for finding the kth largest eigenvector, you have to look for the kth largest eigenvalues of k, then corresponding unit eigenvector divided by the beta k upon root over that eigenvalues, and then you have to take the linear combination with the data set, the data points.
It means if the given eigenvector is not having unit length, do we need to normalize it?
Yeah, obviously you have to take the unit length eigenvector.
Okay.
So is it okay if we can solve one right now? I mean, using this algorithm?
One question you mean?
Yeah, I mean some
example. So finding eigenvalue, eigenvectors takes time. So it's not good to take questions here, because it will take more time, and we need to cover more weeks as well.
Okay, so in the exam we should not expect us to calculate these things, right?
For not exactly the lengthy calculations, but you should know how to calculate eigenvalues, eigenvectors, corresponding eigenvectors. For matrix up to 3x3 matrix, that should be easy, right?
Okay.
Excuse me, sir. So this beta k is eigenvector of k or alpha k, which is eigenvector
This
k,
is
sir?
of matrix k.
And the alpha k, sir?
Alpha k I'm defining as beta k divided by root over n lambda k, where n lambda k is the eigenvalues of k.
So
Is it clear?
So basically, we are doing the same thing what we were doing earlier. It's just that instead of W1, we now have beta 1. Is it so?
Yeah, their eigenvectors become your principal components,
And
right?
the matrix is different.
The matrix is different, but their eigenvectors becomes your principal components. But here, these are your coefficients, which will give you the which with linear combination with the data points will give you the eigenvector principal component.
So a different matrix, just dividing it by the eigen value
The
root of the
procedure
eigen
is same. You have to again
gives
do the
the,
eigen decomposition, but of the k matrix,
so
and
it
you
becomes,
have to make sure that these alpha k's are beta k upon root over eigenvalue.
so just dividing it by that root under lambda, it is equivalent to what we were doing with the covariance matrix.
Procedure is same, but it's not equivalent thing. Here we are finding the coefficient, there we were saying that eigenvectors are actually becomes your principal components.
Using that we are finding out WK, isn't it? So sir, it has to become equivalent.
Equivalence means what? What do you mean by equivalence?
Like what we were doing with that covariance matrix X transpose, since it was difficult for if the dimensions were very high, like D was very large, so we are using another matrix just to reduce the work that we are
Yes.
doing, and then that alpha, so what we are getting is that the alpha k, we just have to change the scalar value on the alpha k, the scalar that we have to multiply each vector to. Is it so, or whether I'm not understanding it? I don't understand.
So I didn't get what do you mean by equivalence,
So
but both the algorithm, the standard PCA and whatever we have done here, the algorithm goes in the same manner. But there we call those eigenvalues, that whatever we find alpha k or whatever beta k, let's say for covariance matrix C, we call it the principal component, right? These beta keys or alpha keys are not your principal components. This gives you
the
remember,
coefficients.
yes. So remember, we are calling
Coefficients.
that W keys are we can return as the linear combinations of the data points,
Yes,
right?
sir. So
So
these alpha k's
these
are the
coefficients.
coefficients.
Yes, these coefficients.
Okay, so sir, we are trying to find out that coefficient so that we can work with the WK. That is
WK,
what we are doing.
yes,
Okay, sir.
yes. Okay. So
Excuse me, sir.
yes.
Yeah, sir, just one quick question. We are going through all this algorithm just to avoid calculation
Eigen decomposition complexity.
of covariance matrix, right?
Yes.
Okay, got it.
Okay.
Excuse me,
So
sir.
suppose it is a 3x is a 3 cross 3 matrix. Then following all the steps, we will calculate till alpha k, and k here will be maximum 3. If suppose there are three distinct eigenvalue, correct?
Okay.
Then wk. So if I have to calculate w2, so what will be w2 here in the fourth step?
So for if you go along with this algorithm, you have to find x transpose x. Then you have to find that second largest
Yes.
eigenvalue. Let's call it lambda 2.
Find the beta
Okay.
2 I will
Now
find.
corresponding eigenvector of unit norm. Let's call it beta 2 of unit norm. Okay.
Yeah.
So remember this is
Then
of
I will
unit norm.
find out alpha 2.
Then you will find beta 2
3
root over
lambda.
lambda 2,
And is 3 here, so
right?
it will be 3
And
lambda.
take the linear combination with x. No. So you just take the here this lambda k are the eigenvalues of C.
Correct.
Right?
So it is
And this
beta
and
k
your
by root over n lambda k. So if lambda 2 I am using, so I have to use 3 lambda 2, no?
no. So here I am find lambda. I am find the eigenvalues of x transpose x, not of x transpose. Here lambda k is the eigenvalues of x transpose. If you have found eigenvalues of x transpose, then you can take 3 lambda k. But what I have done here, I have found the eigenvalues of x transpose x. So this is n lambda k, right?
So for x transpose x, whatever lambda we are finding, those are n lambda k.
Yeah, n lambda k's. Remember the eigenvalues of x transpose x and x transpose are same, right? And your covariance matrix is what? 1 by n. Okay, so
So why
whatever
don't we
eigenvalues of this is your if the lambda k is the eigenvalues of this matrix, n lambda k becomes the eigenvalues of
Okay, understood it. Then in step 4, W2 will be?
step 4 W2 will be your linear combination of x and alpha 2. Okay, so alpha 2 remember is a vector of in n dimension column vector.
So why don't we divide X
So what
transpose?
if x we have started, suppose x is a 3 cross 3 matrix, and alpha k will be what dimension?
3 cross 1.
So it will lead to 3 cross 1
3 cross
vector.
1, yeah. D cross 1, right? W case belongs to D cross 1.
Thank you.
So,
okay. Okay, now move to the next part of this. Next part is the second issue, which is actually the non-linear relationship between the data set. Remember, whenever we using PCS, we actually finding out the most important directions, right? Let's say your data set is distributed something like that. Okay, so rather than having these directions x and whatever call it x1 or x2, we are actually finding these directions, right? These directions, and this is actually your PC1, and the orthogonal one becomes your PC2. So we are actually using standard PCA. We are finding these directions and throwing away these actual features, right? So this is true whenever your data live in a low dimensional subspace. So here your data set can be represented using this line, right? So that is what it's mean by it's live in a low dimensional linear subspace. Let's assume your data set is not linear in nature. Assume some data set is distributed something like that. Now, what will be your direction which gives you the maximum variance, or let's say it contains more information? In this case, where your data set was linearly related, you can say that this directions will give you the most important or say this captures the most importance of the data or most variance in the data set. What about this data set? Will it be this one or this one? Or and there may be many directions which captures the highest information or highest variance in the data set, right? So there is not such unique directions whenever your data set is not linear in nature. So how to resolve these issues that we are gonna see in this next slides. Okay, so this is what how your data for one example, this is how your one data set is distributed. So this is the same equations of circle equation, where this is not centered one with some radius a and b, with some center a and b, and with radius whatever 1 minus a square minus b square, whatever that is. Okay, so this is your circle equations. Your data set is related something like that. Now, so our task is to, if we can somehow transform this data set into the higher dimension such that this data lives in a linear subspace in that dimension, then we are done. Because whenever your data set lives in a linear subspace, you can easily apply the standard deviation there. But if we don't have we don't have the linear relationship, can we transform those data set into higher dimension there, such that it becomes linear in that higher dimensions? If we can somehow do that, we are done, right? So we have to find this such transformations. Can we do that? Let's consider for this particular examples, if my features are f1 f2, the relationship between non-linear, it can easily be said that it's the quadratic relationship here. So if we transform these features into such a way that here it's from r2 I'm going to r6, such that f1 f2 goes to f1 square f2 square, f1 f2 f1 and f. So now these are your features, f1 square f2 square, f1 f2 and constant, and f1 f2.
Just 1 second, one doubt. In what dimension this data lies in? Now R6 data.
Yeah, if we transform using this, if we transform our data set using this mapping, then your data may live into the R6 dimension. Okay.
Actually, in GA, one question is there. The data lies in the lower dimension, right? It's in 5-dimensional space, like that it's given.
Yeah. So you can think as because you were able to find such one u such that this phi x transpose u is equal to 0, right? So you can call it. Just think about the space three-dimensional space, and you have one plane, right? So if you can and for a plane, you can always find a vector which is perpendicular to that plane, right? For any plane. So if you are able to find such vector that phi x transpose u is always 0 for all those data points, then you can claim that these xi's are living into some lower dimensional space of that, actually in that R3, that data set are living in a plane.
How
Because
can we
you can
say
also,
this data lies in 5-dimensional space? That I'm not able to
yeah.
understand.
So once if you have found such u such that this phi x transpose u becomes 0, phi x transpose dot u becomes 0, So it means that you have one direction such that this dot product becomes 0. It means that your all the data points becomes orthogonal to this vector, right? So all these data points are lying into the R5 some hyperplane in R5. This hyperplane belongs to the R5.
R5
No, sir.
particularly or R4 also? I mean, could you please explain that?
No, R5. This the plane. If your data set is lying in the R3 and they are lying in the plane of R3 space, then that plane actually is your two-dimensional plane, right? The dimension of that plane is two-dimensional. And if you are in two-dimensional, the line is the line itself is one-dimensional, right?
So is it always
Yes.
less than 1?
So
Less
is
than
it, yeah, if dimension is D, then it will be D minus 1, you are saying?
yes. That the dimension of that plane or hyperplane.
Why
Plane
D
in the
minus 1
two.
only? Why not D minus 2?
Why not D minus 2?
Just because that this U, right? This U is at
Actually, the question is in graded assignment. The answer says the data transform data points will lie on a 5-dimensional subspace of R6. So R6 that is fine, but why it is 5-dimensional? It may
Yeah, that's
be
what I'm
4 or
asking the
maybe
same.
3. That is the
that
question.
that U
That
is
how can
derived
I
from
know that
the
it is
If
5?
you can visit that question right now, it will clear up the doubt.
No, the same, the data is same. What he gave the statement, now that's itself.
No,
The
okay.
transform data points will
I got
lie.
your doubt. So just think about the three-dimensional space and let's consider your data set is actually living in a plane. Okay, and for a plane you can always find a vector such that x transpose u becomes 0, right? These xi's are living in a plane. So if you are able to find such u such that this becomes 0 for all such data points, then your data points are lying in a plane, right? What if xi's are living in a line in that is R3 space, three-dimensional space? Then you have more than one u, right?
So there has to be only one U.
Uh,
Like,
no, this directions. In this direction, you can take any vector,
so
which
there
will
could
give you
be
this.
two such U which is orthogonal to this. That could be possible.
But the directions will be this one only. Vectors is denoted by two quantity. One is the direction, and second one is that length, right? So take any vector in this direction. It will always give you the dot product to be 0.
Excuse me, sir.
Is it clear? Okay, so for now, just consider that if you are able to find one direction such that this phi x transpose u becomes 0, then you can call this data point phi x1, phi up to phi xn are living into a hyperplane. Which if these phi's takes you the d-dimensional space, then this hyperplane actually is in d minus 1 space.
Is this U unique?
Not unique. You can take any vector in this direction.
Okay.
Excuse me, sir.
Excuse me, sir.
Okay.
So this
Sir,
U, we can say that for a given non-linear function, it will be like unique, right?
Can you please come again?
Like for a given non-linear function, it will be kind of unique, right? It will lie within a fixed range, right? This U.
No, it's not unique. Take any vector in this direction. What do you mean by a unique vector? It's just
No,
take
I mean,
different, yeah, with
yeah.
different.
Yeah, it can be any scaling along that vector. I
Yeah,
mean, that particular line will be unique. Right? That
yes.
U will be unique for a given non-linear relationship.
Even the parallel ones, right? If you think as vector as a line, the parallel ones will also again will give
Yeah,
you this
any
product.
scaling
Yes,
along
any
that
scaling.
particular
Yes,
space.
yes.
Excuse me, sir.
Even the negative direction of that will also give you the zero, right?
Yes, yes.
Excuse me, sir.
Yes.
Sir, the output of the transformation f1 square f2 square, that particular vector in R6, the order of the data points in that vector, is it fixed or can we move them
No,
around?
no,
And
no. It's not. It's just that different features. This is your one feature. This is second feature. This is third features. It's just different features, right? Initially you have one feature, have two features. Now you have these features.
okay, so if we move about these features in R6, then the like according to them the U will also change, right?
Yeah, according to, because you want this phi x transpose u to be 0, and actually this product is corresponding product and then summation, right? So this become f1 square plus f2 square
Yeah,
and
yeah.
this 0. So according to that equations you can do manipulations of this
But
given
phi
product.
remains same in all cases, right?
Yes.
Okay, okay, got it, got it.
So,
Hello, sir.
the only takeaway from this is that you can find such such mapping from one dimension that takes your data from one dimension to the higher dimensional space, such that data, now your data phi x size lives in a linear subspace. Okay. Now, since we can find we have the data set which lives in a linear subspace, we can now apply the standard PCA on this data set now and get your principal components, right? So now your this data points phi x1 up to phi xn live in a linear subspace, and now you can apply the PCs on these data points, and you can get the principal components. So remember, this phi xi need not to be centered even if the xi is centered. So you have to again do the centering for this data set, and then you have to apply the standard PCs. Okay, so if you apply the standard PCA on this data set, remember your K matrix becomes now phi x transpose phi xj, right? This is how you define the K matrix, where the ijth element is your xi transpose xj. Now your data point are nothing but phi xi and phi xj, so your K matrix becomes this thing, right? So for everything you have to do the computations. For every data point you have to transform it into the higher dimension and do the dot product computations and all. So there is a clever way to skip all these computations, and we can easily find this K matrix using one method, using the kernel functions. So how you define the kernel functions? A kernel function takes two vectors and operate upon those vectors. And a function from RD to RD is called a kernel. If you can find a transformation mapping from RD to some higher dimensional space, such that this function is actually nothing but this phi xi transpose phi xj, then you call K as a valid kernel. Okay, so if we have such kernel corresponding to any phi, we can find this K matrix, right? Because in the K matrix, remember, this is actually nothing but your K xi is xj. Okay, so for K matrix, if you have kernel for any transformation mapping, if you have the kernel function, then you can find K matrix, and you need not to worry about the, what mapping actually is, right? So this is the clever way to find the K matrix without even knowing your what actually transformation is. So that's the use of kernel function here. Okay. So one point here that I want to make is that you have to if you have been asked to check the validity of a kernel function, you can go into two methods. One is you have to if you can find the appropriate mapping such that you can verify these equations for all the data points, then you can call that K as a valid kernel. Otherwise, you can go in the second manner as well, where you have to check these two conditions. You have to check whether this kernel function is symmetric or not. So you have to check whether Kxi is same as Kxi for all the data points, right? And the second condition is that the K matrix, this K matrix is positive semi definite. Okay, so if you have checked these two conditions, then you can call the K kernel function as a valid function. Okay, so for checking validity of a kernel, whether if you can easily see that mapping, then fine. If not, you can explicitly find that transformation mapping. Then you have to check these two conditions. Okay. Now, since we, if for a particular mapping, if you have kernel functions, then our task is done, right? Because now we have the kernel matrix, and now we can apply the same algorithm that we have already discussed, right? So, and what was your algorithm there? You find the kernel matrix K using the kernel functions. And one more point here is that we haven't centered our data set, right? So you have to make sure that your data set is centered. So rather than doing the data points, making data points centered, you can use this function. This KC is actually the center matrix. If you apply this expression there, then your KC is actually the matrix which is correspond to the K matrix of the center data set. Okay, where this in is actually the n by n matrix with all the entries to 1 by n. Okay, so that's how you make sure that these data points are centered. So first step was you have to find the matrix x transpose x. So here in this case it's become phi x transpose phi x. Second, you have to make sure that data points are the centered. So for centering the matrix, you can use this equation. The next step was you have to find the eigen decomposition of K matrix, right? So you have L different eigenvectors, eigenvalues, and corresponding eigenvalues, right? Unique eigenvectors. Now your coefficient was beta k. The same algorithm it goes, right? Beta k divided by root over eigenvalues. And so your principal component become the linear combinations. So for finding principal components, you have to take the linear combination with the data points, and your data points are phi x, right? But so for finding your wk, you have to know phi, right? And we want to avoid to do such computations. So it's not, wk can only be computed when you have phi with you. Okay, so wk's we generally don't find in the case of kernel pca. What we find the projections on those PCs. And remember, what is the projection of that ith data point on the kth principal component? It's just the phi x transpose wk. So this is the projections of the data point phi xi on wk, right? And how it is, if you write alpha wk as phi x alpha k, you can see easily verify that this becomes your this quantity, right? So this is nothing but from there, if you find this alpha k, so alpha k, let's call this vector as alpha k1, alpha k2 up to alpha kn. So this becomes your vector. And so if you have to find the projection of the jth point, so let's call this jth point as at phi axis. So what you have to do, you have to find alpha k1 kernel matrix of phi. So you can call it xi xj. So x1 xj plus alpha k2 k x2 xj, right? So this is how you go. And this will give you the projections of the kth point on the jth point on the kth principal component. Okay. So this is all in week 2. We have 2 issues, and we have resolved both using the Bun algorithm, right?
Excuse me, sir.
Yes.
Sir, I have doubt in graded assignment 2, question number 3.
Okay. I think we have discussed it there, right? This thing. Whenever you have found one directions such that this phi x transpose u becomes 0, then you can call this phi xi are living in a hyperplane which is actually a d minus 1 dimensional hyperplane.
Yes, sir, I understood this part. And sir, but there is another point. There will be some W belongs to R6 that all of the data points are orthogonal to. So this will this R6 W which belongs to this R6 dimension, all of these data points will be orthogonal to the same subspace.
What are your wk?
So we are having this second point in question number 3. There will be some W belongs to R6, that all of the data points are
Yeah, so
orthogonal.
there this W is actually U that I mentioned here.
Okay.
Okay.
So
So
all
some
the
different
points would be
methods.
orthogonal to that W.
Yes, yes. Not W, that yeah. So that all the data points will be orthogonal to that direction W.
Okay, to the direction of this. Okay.
Yes, yes.
Okay, sir. Thank you.
Sir, I have a problem in graded question number 9, week 2.
Okay. What is doubt here?
Sir, what is a projection? Projection is X transpose W into W.
If it is mentioned projection, then projection may be one scalar quantity that gives you the length of that projection. And if you are interested in that direction, then it becomes that you have to multiply that scalar quantity with the direction, right? That WK direction.
WK. Okay, so this we have to solve without that direction W.
Yeah. So here in this particular question, it is mean that length you have to find.
Okay, sir. Okay, sir. Thank you.
Hello, sir.
Yes.
Sir, what type of questions you might be asking in the quiz?
So better to solve all the activity questions, practice questions, graded assignment questions. That will be sufficient for your practice for quiz.
Okay, and
And go through all the concepts which are discussed in the lectures.
okay, and will questions like starting from the calculating kernel K X transpose X and going up to W, calculating W, these type of questions will be asked, or
So any calculative questions will, if any calculative questions are there, that will be easy calculation, not a lengthy calculations will be there. Okay. Some questions will be definitely will require calculations, bit of calculations, but not that lengthy calculations.
okay.
So one more question. Where you have written the formula for K centered. Can you show that?
Case can centering of kernel, is it?
Yes, sir. Yes, sir.
Okay.
So the fourth term has a small k. What is that small k?
Oh no, it's not a small k, it's capital K. Matrix K. It's matrix K, okay.
Okay, sir. Okay, sir. Thank you.
Sir, could you please explain the fifth question of second graded assignment?
Can we take questions later after week 3 and week 4? Because we are already running out of the time.
Yes, from it we have MLF.
Yeah. Okay, so I think we should move on the week 3.
Shall I move on?
Yeah, yes, sure.
Sure. Okay. Yeah. Let me share my screen. Okay, hello everyone. Can somebody please confirm whether my screen is visible?
Yes, ma'am.
Yes.
All right. Okay, so we'll now go over week 3 contents. So what have we been doing? We've been doing unsupervised learning, and as we know, the motive of unsupervised learning to find some patterns in data. And in weeks 1 and 2, the kind of patterns that we were looking for, the kind of pattern that we were looking for was finding the principal components, as we know, and then these principal components are ultimately used for reducing the dimensions in data. So that's one kind of pattern that we've been looking at. There could be some other patterns that we can probably look at in the data. So the other one that we can see is whether the data points in the given data are clustered together or not. Okay, so that's a useful pattern to look, because it will tell us whether there are some data points which are alike or not. So we can see that, right? And that could be useful. And you might know several applications. So given some data points, how you can, group them together based on how similar they are. So that's one useful application. So that's what precisely what we are looking at in week 3, that's clustering. So formally putting, we are given some data points, and our aim is to partition them into some number of clusters. Let's say k clusters, right? So let's say there are some data points, right? These kind of clusters we are looking at, right? So this is the data is given to us. How can we automatically find the clusters in the present in the data, right? So that's the motive here. Now, let's say I give you this kind of data, and you have to form of course you cannot visually see them, right? This data is in 2D. There are only 2 features, feature 1 and feature 2, and you can see, and obviously there are 4 clusters, you can look at it. But in general, the data will be huge. There'll be many features. How can you automatically put the data points in different clusters is what we are talking about. If you have to do brute force, what do you mean by brute force? You try all possible combinations, okay? Which means let's say k is given to us. Let's say k is equal to 3 is given to us. You put the data points in 3 clusters. You try out all possible combinations, okay? Now, if I ask you, how many possible combinations will be there? Let's say if n is equal to 100, and you have to cluster these 100 data points in 3 clusters, how many possibilities will be there? If let's say I tell you that the clusters can be empty. So each data point has 3 possibilities. Each of these 100 data points has 3 possibilities, right? So 3 to the 100 is the total number of combinations that you would be expected to try. Okay, that's a huge number. So obviously we cannot go with the brute force method. Now, just continuing our formalization of the problem, there's one more thing that we will be talking about. So let's see what that is. So we'll be using cluster indicators. This very thing, cluster indicator. So Z1, Z2 are the cluster indicators. Z1 is the cluster indicator for the data point 1. Z2 is the cluster indicator for data point 2, and so on. And each of these Zi's can be only any of the values between 1 to k. K are the number of clusters. Okay, so I hope this is clear. So for each data point, we have a cluster indicator, and that will indicate which data point which cluster this data point belongs to. For example, Z5 is equal to 3. That means X5 will go to cluster number 3. So, all right. Now, I told you that if you have to try all possible combinations, there are k to the n possible partitions that you will be expected to try on, which is a huge, which will take a lot of time, not possible. In fact, it is an NP-hard problem, okay? And we know what is an NP-hard problem, a problem which has no linear time solution. That's an NP-hard problem, which is precisely what this is. So what we are trying to do right now is we are trying to look at whether we can do something better, whether we can come up with some algorithm that can reduce the amount of time that can be taken and provides us some clusters as well, which are good enough. Okay, so that's what we are looking at right now. Now, let's say I give you some cluster assignment. What do I mean by that? I give you some values for these cluster indicators, right? Some set I provide you. Can you tell me how good that is? Basically, what I'm asking is how can we check how good a given partition is? Okay, so let's talk about let's formalize the problem even a little more. Let's talk about the objective function of the problem that we are talking about. Let's say this is the objective function, capital F. Of course, the input is Z1, Z2, Zn, which is dependent on X1, X2, Xn. Now, what is our motive? Getting back to the kind of data that we have, a good cluster will be 1. Let's say these are the clusters that we can see are prevalent in the data. So why are these good clusters? Because every data point in a given cluster is close by to the other data point in the same cluster, right? So the distance between the different data points is very small as compared to their distance with the other clusters, right? Or in other words, if you, let's say, have the means of these clusters, let's say this plus indicates the mean, the distance of each data point from these means is small, right? That can be a good indicator to tell whether cluster assignment is good or not. So that's what we are doing here. I mean, based on what we just now discussed, we are coming up with an objective function, and this is what it is. For each data point, we will measure its distance from the mean of the cluster it is assigned to. So this mu of Zi, if you understand what Zi is, you will know what mu Zi is. So Zi is the cluster that is assigned to Xi. So mu Zi is the mean of that. Now we are finding the distance of this data point from the mean, and we are squaring it up and we're summing it up. So for each data point, we are checking their distance from their means, and we're summing that up. So that's basically is our objective function. Now, obviously, we need to minimize this value, right? We need to minimize the distance of each data point from the means of their own clusters. So this is the objective function that we will be using. And formally speaking, what will be the mean of each cluster? Formally, we can write it like this. This one is an indicator function, or indicator variable also it is called. How do we read it? This thing, if this is true, the output will be 1. If this is false, the output will be 0. Okay. Now, how do we compute the mean of a cluster? Let's say this cluster we're talking about. How do we find the mean of this plus value? How do we get it? So for each data point, you sum that up and divide by the number of data points in that cluster. So let's say the first data point is 1, 2. The second data point is 3, 5. Third is 4, 6, and so on. You sum these up, whatever you get it, and then you divide that with, let's say, 9 data points, 1 by 9, right? So basically what we are doing is we are summing up the Xi's in each cluster, this very thing. We are summing up the Xi's, only those Xi's which belong to the cluster K. So we are talking about the mean of cluster K. So obviously we want to only sum up those data points which belong to cluster K. So Xi multiplied by 1 indicator function, Zi is equal to is equal to K, right? The denominator, like I said, is the total number of data points that belong to the given cluster. So this will give you not n, the number of data points belonging to this cluster K, right? I hope that is clear. So just the formalization. The idea, I guess, should be clear now. Now, like I said, we need to minimize this. So this objective function we have understood, we have to minimize it. And I also told you, if you try all possible combinations, it's going to be a very difficult problem. It's an NP-hard problem. It will take forever to give you the best values. Okay. So we are looking for an algorithm that can use some strategy. And that algorithm that we're looking at in this week is K-means, also called Lloyd's algorithm. This algorithm gives you a solution which probably may not be optimal, but is good enough. Okay. And the strategy that this algorithm uses is sort of greedy. Okay. If you have seen the different kinds of algorithms, greedy, dynamic, right? So this one follows a sort of greedy policy. And let's try to understand what is the sequence of steps that this algorithm follows. So what we do is, as the first step, we initialize. So these are the cluster indicators that we know. The 0 superscript indicates the iteration. So this is an iterative algorithm, first of all. So in the very first iteration, we do the initialization and we randomly assign the clusters to each data point. Okay. To each data point, we'll assign some clusters randomly. Okay. So Z1, Z2, Zn will assign some values randomly. So each data point now belongs to some cluster. Obviously may not be good, but we do some initialization. Now what we do is, in every cluster we have some data points, right? After this initialization. Okay. We check. So firstly, we compute the mean of each cluster. Okay. After doing this initialization, you compute the mean of each cluster. Okay. Now, after we do that, we check whether people are happy or not. That is, we check whether each data point is in the right cluster or not. That is, we check whether there is a data point which is present in some cluster. So this is, let's say this is the mean of this cluster. And let's say this is the mean of some other cluster. This is a stupid example, but that's fine. So for this data point, we'll check the distance of this data point from this mean and the distance of this data point from this mean. Now here in this case, the data point's mean is closest as compared to any other mean. So this data point is happy. Okay. On the other hand, let's say we have some data point like this. Now this data point has been assigned to this cluster, and the mean of this data point is cluster is this mean, right? So if you compare the distance of this data point from some other mean, this is smaller, which means this data point is not happy, which means this data point will want to move to this cluster in the next iteration. Okay, so that's what we do. So after computing the mean, we do this reassignment. We do this reassignment for unhappy people, right? For people like this one. So what we do is, instead of this this cluster, this data point will move to now this cluster. So in a given iteration, there will be some reassignments, such reassignments that will take place. Okay. Now, after these reassignments that take place, obviously, the data points in each cluster will change, right? So the next obvious step will be to recompute the means, which is what we do. So these two these two steps will keep going on and on until what? Until convergence. Okay. So in the end, what will happen? Every data point will be happy in their own cluster, which means every data point's distance from their own mean will be the smallest as compared to their distance from any other mean, right? So that is what is the k-means algorithm. These are the sequence of steps. Now, I'm telling you that until convergence, so we are not sure whether the algorithm will converge or not, right? Well, we can prove that this algorithm converges, okay? Now here, given the time, I'll give you the broad idea about how we can say that this algorithm really converges. Now, given the construction of the algorithm, like I just now told you, when would a reassignment happen? This data point moved to this cluster. This reassignment happened only because its distance from its own mean was more than the new mean. Okay, so after this reassignment, this data point will be in a cluster where its distance is small, which means the overall distances are going to reduce, which means the overall objective function is going to reduce, isn't it? So in every iteration, only those data points in cluster which are unhappy, right? And when they move, their distance from the mean reduces, and hence the value of the objective function reduces, right? Now, another thing to note is that whenever any reassignment happens, it results into new partition, isn't it? So earlier this data point was here, now this is here. So it's a new partition, of course. Now, we initially discussed how many total possible partitions are there. There cannot be more than k to the n partitions, right? So even if we think that this will keep going on and on, it has a limit, right? Up to k to the n. There cannot be any. So after this, if there is any new partition comes in, that will actually be the same as something that came before. So the objective function value here and here will be same. So it doesn't make sense as per the construction of the algorithm. Okay. So the finiteness of the number of partitions, it clearly explains that the algorithm is going to converge after some number of steps. Okay. All right. Now let's talk about what kind of clusters will be produced by this algorithm. So there are actually many clustering algorithms, right? We are covering only k-means here, and probably the kind of clusters that are created by some other technique will be different. So here, knowing how k-means works, let's see what kind of clusters will be produced. Okay, so let's say these are two means, okay, and let's say this is a data point. Now we will look at the distance of this data point from these two means. This data point is closer to this mean, so obviously it will be in this cluster. This is cluster C1, cluster C2, right? This will be true for all the data points. This will be true for all the data points which are closer to this one. Similarly, if there are data points which are closer to this mean, they will be in this cluster. So the kind of boundary that will be there between two different clusters will be formed how? You join the means of two clusters, and then the perpendicular bisector of that line will be the boundary between the two clusters, right? Now let's say we don't understand how this will be a perpendicular one, why not some other line, why not some other boundary. So let's say this is green one is the boundary. Now let's say there is some data point, this one. No, not this one. Let's take this one. Now this data point, you see the distance of this data from this one and from this one, this data point is closer to C1, right? But given this green boundary, we are actually putting this data point in the cluster C2, which doesn't make sense as per the construction of the algorithm. We look at the distance of each data point from the means. So wherever it is closer, it will go to that mean. So which means this data point is going to go to this cluster. So this boundary is going to shift, right? So even if you take any other case of any other example of the boundaries, the things will be not fitting as per how the algorithm works, right? So this will be shifted here. So the perpendicular one is the perpendicular boundary is the one that will actually come out as the algorithm proceeds. Okay, so this is an example of two clusters. There could be many clusters, right? Let's take an example of 3 clusters. Now let's try to look at what kind of boundaries they will have. So join these lines and the perpendicular bisector, and then join these lines and again the perpendicular bisector, and then join these lines and perpendicular bisectors, right? So these are going to be the regions, right? I hope this thing is clear. So this is going to be the first cluster, this is second, and this is third, right? So if you get any kind of so these are called Voronoi regions as well, right? So this is region for this cluster, this region for this cluster, and so on. Now, if you get, let's say, some other kind of division that is not going to be valid as per k-means, probably some other clustering technique might be producing such kind of regions, but not k-means, right? So you should see the line and you should see whether this is 90 or not. So this is an idea to see what kind of clusters will be formed. Now,
ma'am, one thing just
yeah.
The Voronoi region, if there is only 2 means, the earlier example.
This one, yeah.
Yeah. To say the region is Voronoi, we must have these 3 means.
No. This could be this is one Voronoi region, this is another region, right?
Only thing, it has to be
divided by half spaces.
Linear,
yeah, divided by this one half space. There's only one half space possible between 2 clusters, so that will be the region that will be formed.
And is it necessary that the space get divided by a line only, or can a plane, when a plane...
No, this is C2. Sorry, this is D is equal to 2 here, right? No, sorry, K is equal to 2 here. Over here, K is equal to 2. So how are you able to see here? Because there are 2 features, right? Feature 1, feature 2. So basically this is 2-dimensional data, right? The K is equal to 2, but also D is equal to 2. That's how you're able to see these data points. Let's say D is equal to 3. Then your data points will be in 3 dimensions, and then there'll be a plane. Okay. And if D is more than 3, then there'll be a hyperplane. So you can generalize that way.
So K minus 1 half spaces. So it will be difficult to imagine beyond 3 dimensions.
Right. That's why we are taking the example of 2 dimensions, but 3 you can imagine. More than 3, if you understand up to 3, that's fine. You can generalize beyond that. If you understand
so
this
if
part,
it is three dimensions, then there will be 2 planes which will be creating the clusters.
2 planes. How many? What is K in 3D? What is K? If K is equal to 2, then there'll be one plane that will be dividing the 2 clusters. So let's say these red ones, don't consider the blue ones. Let's say this is one cluster, this is another cluster. So there'll be one plane, right? This is very bad example, but you get the idea. There'll be one plane. The data is in 3D. This is feature 1, feature 2, feature 3. And these red points are the data points. And K is equal to 2. So this will be one cluster. This will be another cluster. But since the data is in 3D, there will not be one line that will be separating them. There'll be
what if K is 5 in 3D?
If k is equal to 5, then there'll be multiple planes which will intersect and hence will produce the Voronoi regions. K is equal to 5, so k minus 1 half spaces, which means 4 half
So
spaces.
do they always need to intersect, or they can be
See,
parallel
they're
also?
endless, right? They will intersect somewhere, right? They're endless. They're not small. Somewhere they will intersect, right? I mean, they're not limited in their length, right? Half spaces are like that. I hope that's clear to you.
No, what I was saying, it could be a 3D, but there will be clusters which are separated by parallel planes. Can that be?
There will be clusters which will be separated by parallel planes, is it? Can you help me with some such an example?
No, I'm just trying to visualize.
See,
That
firstly, k-means will never produce such clusters where the whatever you said,
Parallel
the
planes.
parallel planes, right? That will not be possible. K-means will not be able to produce such clusters given how it works. Okay.
okay.
Ma'am, what happens when the point is on the perpendicular bisector? I mean, which cluster?
Okay, yeah, good point. So, see, in that case, let's say this point, which has equal distance from both the means. See, if you see the sklearn implementation, they do it randomly. So randomly, this point will be assigned either to this cluster or this cluster. If you're coding yourself, you can use any strategy. But I think random is this is a tie, right? So practically, sklearn does it randomly. One of these clusters will be assigned in that case.
Okay.
Yeah. All right. So that was about the kind of clusters that will be produced. Now, in the first step of k-means, we talked about the initialization of the cluster centers, right? And we didn't talk about how we would do that. So one obvious thing is to do it uniformly at random, right? And that's what we do in k-means. But there's one more thing that you should know, that k-means may not see k. Let me write it down. K-means always converges. That is fine. But there's another thing that you should know is k-means may not produce optimal clusters always. May not produce optimal clusters, right? Always. Sometimes it may produce, but sometimes it may not produce, right? So one of the reasons could be the initialization, right? So if you look at, so I'm doing it in 3D, but you visualize in MODI. So 2D I'm doing. So let's say this is your objective function. Okay. What are we trying to do? We are trying to minimize the value of this objective function. And let's say this kind of structure this objective function has, right? So there'll be some value of there'll be some initialization that we will do, right? So depending on what kind of initialization we do, where we do the initialization, let's say we do it here. So in several iterations, the value of the objective function will come over here, okay? And we settle here. K-means will stop here. It will converge over here. Now, this is the global minima. This is the local minima. So if you start from here, probably you'll get the optimal solution. But from some other point, probably you might not end up in the global minima. So the clusters that will be produced may not be optimal. So in practice, what we do is we run k-means multiple times. Let's say 10 times. I think sklearn does it 10 times by default. You can control it. Well, so in practice, you run this k-means multiple times and you note the value of the objective function, which was capital F, right? Whichever gives you the least f, that's what you proceed with. Okay, so that's what we do in practice with k-means. Now, since we know that the initialization of these cluster centers is sort of important, so why not do it intelligently is what we are doing in k-means plus plus. So k-means plus plus.
Ma'am, one question in the previous slide you showed, right?
Yeah.
In k-means, 10 times in that initialization happened randomly, or how is it?
Randomly, yes, randomly. K-means does it randomly. So k-means plus plus tells why not do it intelligently, right? Now, what kind of intelligent allocation of clusters can you think of? See, we've been saying that the good clusters will be those where the data points are, closer to each other than the data points in some other cluster, right? So let's say I initialize the cluster centers all here. This could happen, right? If you're doing it randomly, this could happen. So after several iterations, k-means actually could give you good clusters, but may not give as well sometimes. Okay, so but if you initialize your cluster center something like this, probably you are guaranteed to get the optimal solution. Okay, so that's what we are trying to do using k-means plus plus. We're trying to intelligently assign initialize the cluster centers. So how do we do it? So let's see the procedure first, and then we'll discuss. So we initialize the first mean uniformly at random, only the first mean, okay, not the rest. Now iteratively we'll choose the subsequent means also. How do we do that? So let me give you an example, and then this will not be necessary. So let's say these are the data points, okay, and we choose one of these as first mean. Let's say this one we choose as the first mean. Okay, now we have to choose the other means. All right, let's say this is your x1, this is your x2, this is x3, and this is x4. We want that point as the next mean, which is as far away as possible from the mean that we have already chosen. Okay, so what we'll do is we'll check the distance of each of these data points from this existing mean, and the square distance will be their score. Let's say this is the distance 10 is the square distance of x1 from mu1. Let's say this is 20. This is not making sense, but it's okay. Let's say these are the distances. Now these distances, square distances, are the scores. And then what we do is we convert these scores to probabilities. How do we do that? We normalize it. 10 plus 20 plus 30 plus 40, 100, right? So 10 divided by 100, everything divided by 100. Now this becomes the probability. Now with this probability, we will choose one of these data points as the next mean. Now since this has the highest probability, this point is likely to be chosen as the next mean. But this is only probability, please note. Probably this can also be chosen, but the likeliness is less, right? The chance is less. So this is how it works. Well, this was an example of one mean, right? So far only one mean was there. Now let's say we choose this as a second mean. This becomes your mu2. Okay, now in the next iteration, this x1, x2, or x3 could become the next means. Now how do we do? Please note this. For each data point, we check the distance from each mean, which means for x1 we'll check its distance from mu1 and mu2, and whichever is the smaller, the square distance, whichever is the smaller, that will be the score of x1. Similarly, for x2, we'll check its distance from mu1 and mu2. Whichever is the smaller square distance will be the score of x2, and same goes for x3. Okay. Now, out of these three, whichever is the maximum, okay, that will have the highest probability of getting chosen then as the next mean. Okay. So I hope you can generalize whatever we just now did. You can do that also. All you have to, keep in mind is that from all the existing means, you have to find the distance, and the minimum of those will be the score. And after that, you can convert them to properties. Any question here?
Yeah, ma'am. The probability you calculated earlier had just one. I mean, you totaled it up and got to 100. So now say x1 and x2 go to mu1 and x3 goes to mu4, which is mu2, x4. So now what is the total now? It's x1 plus
No,
x2.
they don't go firstly. They don't go anywhere.
I mean,
yeah,
I'm just trying to get the point. What is the total score in that?
Yeah. So let's say, x1 score is coming out to be 25. Okay, I'm messing it up, but you get the point. So
It's okay.
let's say square distance of x1 is 25. Let's say square distance of x2 is 35. Let's say square distance of x3 is 45. How did you, let's say 15. Okay, how did you get this? You got this by whichever mean was
Yeah, the
closest,
highest
whichever mean
score.
was large, closest. Sorry, what? Whichever mean was the minimum, lowest, right, minimum. So there are two things involved. First, you see the minimum, and then you see the highest probability. So please note this. So minimum. So basically, what we're trying to do is the minimum distance should be the largest. Okay, for any data point, the minimum distance should be the largest. We are going to choose that data point as the next mean. I hope you didn't get confused here. So getting back to your question.
Sorry, ma'am. We first said that it should be far from the first chosen means. So how is minimum?
So that is the probability. The highest probability should be
The
chosen.
probability should be the highest. So this, if you get this 40, this means the minimum is 40. The minimum distance of this data point x4 from any mean that has been chosen so far is 40. Probably there are some other data points which, so let's say 40, 50 and 60. So let's say for this data point x4, its distance from first mean was 40, its distance from second mean was 50, its distance from third mean was 60. We take the minimum of these, and that is the score. What does this indicate? The minimum distance of this data point from any mean is, the minimum distance is 40, which means the other distances are going to be more than 40, right? So it is actually, it is safe to take the minimum only.
So here
Which
we
means,
don't convert into probability. After
yeah,
40, we don't divide it by the total.
of course we do after 40. So after we do this for each data point, so for x4 we had 40, 50, 60. For x3 we had, let's say, 10, 20, 30. So 10 will be scored here, 40 will be scored here, okay? And we do it for all data points. And then the highest probability element is obviously the, having the highest probability of getting chosen. So after these scores, you actually convert them to probabilities by normalizing them. And then as per probability, you choose them. So that's the probabilistic part there. Yes.
So best ways to do is like to do this. It's good to draw a table and then keep doing this. So
Yeah,
we can
whatever
keep
works
it.
with you. I messed it up, so sorry about that. But please tell me, I'll repeat this if there's any point of contention. So yeah, just note this. You keep this in mind. The distance of x4 from all the, let's say, three means which have been chosen so far are 40, 50, 60. We'll be choosing 40 as the score because that's the minimum value from any mean. Okay, which means all other values will be larger than this. Okay, so we check this for all data points. Why? Because we want that the next mean is as far apart from all the means that have been chosen so far. Okay, that's why we are keeping track of their minimum distances. I hope that thing is clear to everybody, right? Shall we move on?
So like when we have this u3, let's say mu3, then we compare all the means with x1, like whatever the distance of each mean is from x1, and then whichever is minimum we keep that. And then while doing this probability thing, so we take only the minimum one while adding the values, is it?
This is mu1, this is mu2, this is mu3.
Right.
This is x1, this is x2. Now, mu1, mu2, mu3 have been chosen as initial means. We have to choose now mu4, which should be mu4. Let's say only two data points are left. Okay. Now, listen carefully once again. For each data point, we'll check the distance from each mean. Okay. Whichever is smallest. Let's say square distance is 10, let's say 20, let's say 30. Whichever is smallest, that is going to the score of x2. Same goes for x1. Let's say its distances from mu1, mu2, mu3 are, let's say, 30, 40 and 50. Minimum of these is 30. That is going to be the score of it. Now, intuitively, why are we doing this? Try to understand that. Then it will become more clear. We want that the next mean that we are choosing is as far apart as possible from these three existing means. That is why we are looking at the minimum distance. Now, the minimum distance of this from any mean is 10. The minimum distance of this from any mean is 30, which means this is a data point which is as far apart as possible. So this will have a high, this should have a high chance. So what we do now, we normalize, we get 10 divided by 40, 30 divided by 40. This is going to be the probability with which this will be chosen, and same goes for this. Is this clear?
So now in mu4 will be this x.
Mu4 is likely to be x1.
Acha, okay.
Yeah, it's not deterministic, it's probabilistic. That's what. Okay.
Okay.
All right. Moving on. So now, see, when we are given some data and we have to find some patterns, nobody is going to tell us how many clusters you should look for it. Okay, there is no automatic procedure to get what is the right K for a given data. We need to give this as an input to the algorithm. This is actually a hyperparameter which should be given by the user. It's not a parameter that is computed by the algorithm. So let's talk about what should be good choice of K and how do we find that. So getting back, this is the objective function. I hope this is clear. Now our motive is to minimize this, right? Our motive is to minimize this. Now let's say there are some data points and I tell you that K is equal to N. There are N data points and I tell you K is equal to N. What will be the value of objective function, anyone?
Zero.
There are N
Zero.
There are N data points. Each data point is in their own cluster. So the distance from the mean is 0. So the value of objective function is going to be 0. And our motive was to minimize the objective function value. So we are good, right? Are we good? So we are putting each data point in their own cluster. So basically we are not learning anything, right? We are not uncovering any pattern in the data. Now on the other hand, if I say that K is equal to 1, which means you put all the data points in one cluster, right? Again, we are not learning anything, any pattern in the data. So the value of K should be somewhere between K and 1 and N. Now, let's say K is equal to 5 and I move to K is equal to 6. Can you tell me whether the value of objective function is going to reduce or increase?
Increase.
Is it?
Reduce.
These are the data points. If you put them in one cluster, this will be the mean. The distances are high, right? On the other hand, these data points, if you put them in two clusters, will be two means, and the distances will be reduced. Obviously, the value of objective function will reduce. So if you, as you increase the value of K, the value of objective function is going to reduce, right? Okay. Now, I also told you that if you increase K to be equal to N, it will actually become 0, and this is not something that we want. We want somewhere here. So what we do is we put a penalty for increasing the value of K. Like I told you, as you keep increasing K, the objective function will reduce. So put a penalty to the value of K. So some penalty. So basically we, sort of update this objective function where we add some penalty given the value of K. Okay. So which means as you go from K is equal to 5 to K is equal to 6, there's some penalty that will get added. Let's say 10, some penalty. Let's not get into that. So when you put penalty, the algorithm will be discouraged from increasing the value of K. Okay. So as you keep increasing K, the objective function is going to reduce, but the penalty is going to increase. Okay. So we have to find this sweet point where this is the least. Objective function plus P. Actually, this is the point where objective function plus P is the minimum. So this is the value of K that we are looking for. So this is how we find a good value of K. Okay, this is what we have discussed. Yeah. Any questions? All right. If there are no questions, we can move to week 4. Karthik.
Ma'am, one question.
Yeah.
In practice assignment, week 3 practice assignment, question number 6. I have a very particular doubt.
Yeah. Tell me. What is it about?
The question asked, with respect to Lloyd's algorithm, choose the correct statement. One of the correct option, they said, the change of value of objective function indicates the, no, not this one, 1 minute. Yes, F.
Second last option?
No, how the F is correct? The K to the
what is
power
F?
n is only the upper limit of
last
number.
Option, is it?
Yes.
Yeah, for partitioning n data points across K partitions, Lloyd's algorithm takes K to the n iterations to converge. This one?
Yes,
one?
but even if it is K to the power n, Lloyd has to be converged, na?
So we have to choose the correct statements, and this is marked as incorrect, right? Why is it incorrect? See, K to the n is the upper limit. it's not that k means will take k to the n iterations to converge. K to the n is the very high upper limit to what actually k means takes, the number of iterations. Okay, so here what we are saying, for partitioning n data points across k partitions, Lloyd's takes k to the n iterations to converge. It's not that. K to the n is the upper limit. It cannot go beyond that. But in practice, it actually converges within a few iterations. Of course, depending on the data.
That's right. I am saying a very once in a 1,000 time chance. Since this is possible, you can't rule it out impossible. And there is two things.
Okay, so
worst case scenario.
Probably let's add always takes there. I think then it'll be clear. I get your point. You're thinking that probably sometimes, let's say, 1 in 1,000 it takes.
Yeah, in worst case scenario.
So here our intention is to actually ask it always takes. Probably let me add always, and then it's clear, right? Then we are good, right?
Yeah.
So
and another question.
Yeah.
This is graded assignment question number 9.
Go on. What is it about?
They said that bad initialization can lead to bad overall clustering. Is it true every time?
It can lead to. It's not. It always leads to. It can. I showed you, right? Shall I share my screen? That minima, local minima, global minima.
That part is clear. I am saying is it always true? Because the option they are saying which option is correct, and the statement in the third option is bad initialization can lead to bad overall clustering.
It can lead, yes or no? Can it? Okay.
I think we can reach different minimas. Local minima might be higher than any other local minima.
It's maybe may not be. My point.
And what could be like statement meaning extremely sensitive to initialization? Extremely sensitive means what?
Yeah, extremely sensitive to initialization. So I think there's an example you can
extremely
actually work it
sensitive
out.
in the sense, suppose there are 100 points and we are doing clustering, this is initialization, then towards the end of the algorithm all those 100 points will be say suppose k is 5, so there all those 100 points will go into different 5 clusters. So what is the meaning of extremely sensitive over here?
See, extremely sensitive. So okay, if extremely is not there, is it clear? I mean, do you get the intention of the statement?
I get the idea that suppose outliers are there, then it will.
No, here we're not talking about outliers, I guess, right? There are
the first statement of extremely sensitive.
It's about initializations.
K means clustering is extremely sensitive towards initialization.
Right. Yeah. So
okay. Cluster center
I get your point. You're bringing in outliers because yes, if the initialization is let's say one of the points in outliers, then it'll.
Let us discuss two situations. There are outliers. There are no outliers in the data set.
Right.
Then what does this statement mean?
Yeah, so it simply means that if your initialization is not so getting back to the same thing, if initialization is making you fall in the local minima, then you will eventually get the bad clusters, right? That's what it is saying. So yeah, that's what simply it is saying. And if there is a presence of outliers, then you might actually not be able to come out of
so suppose hypothetically there are 100 points and k is equal to 5 and I run the algorithm and every time it is going into the region of some local minima, may not be global minima, some local minima.
Go on.
Okay, suppose I run the algorithm say 100 times or 50 times and somehow it is going into the same local minima kind of thing, hypothetically, then every time all those 100 points will fall into respective clusters in each run of the algorithm, or every time they will go in some different clusters here and there.
If you're always settling over
hypothetical situation, I'm taking that every time it is going towards the same local minima.
Yeah, if they are settling, if you're always settling in the same local minima, then the partitioning should be same. If there are no ties, right? If there are ties, then there will be some random, random
The
assignments.
word, this phrase extremely sensitive is somewhat confusing to me. That's why I brought this point.
See, what are we doing in objective function? We are finding the distance of each data point from the mean, right? Basically, we are looking at the Euclidean distance, right? And if, let's say, okay, outlier you can bring in, but there are two cases: if there are no outliers, if there are outliers. So initializations, see, there could be different kinds of data, right? There could be bad data points, right? The example that we initially saw was actually good data, right? But they could be bad data, and these are very practical cases. Now, initialization actually will actually lead to different kinds of clusters, right? Here it's actually difficult, so that's another point, what kind of clusters will get produced by k-means. But all we are saying is the initialization could be such that, and the data could be such that you end up in a bad cluster. That's what we are saying. So initialization has an effect, but I think what is confusing you is the extremely part, right? So
Yes, ma'am.
if you want to probably justify that, let's consider the presence of outliers also. Now let's say the initialization is over here, then you might actually get weird final clusters. Probably you can check that out through code also. It's very straightforward. So that's what is meant by extremely there. But you actually might actually get the good clusters as well. It could converge to good clusters as well. So that depends on the data. Extremely is simply saying that, see, the distances are involved, right? So where initializations are there, whether the algorithm converges to the right clusters or not, so that may get affected. That's all we mean by extremely there. Yeah.
Okay.
All right. Yeah. Okay then. I'll stop sharing.
Ma'am, can you please upload the slide, whatever you have used?
These are actually not slides. I quickly noted them down just
So
before the
could you
session.
please share them somewhere, like
Yeah,
week 2
sure, we
shared by
can.
Nitin. Thank you.
Sure, we can do that. Sure, after the session. Yeah, Karthik, you may please continue.
Yeah, sure. Okay, so we assume with week 4. So week 4 we'll try to make it fast. Okay, so it's easier than the other weeks. So yeah, so we have seen these things, and now we come to estimation. Same thing. So the main idea in estimation is that, again, the whole point is to somehow see if we can compress our data set in some way, right? So like clustering and representation learning, what we try to do is we try to model the data generation process. So what we mean by this is we ask these questions, right? So what is the process that generates data? So where does the data come from is actually not a correct question, but so what is the process that generates the data is one question we ask. And the moment we ask that question, we have to ask the subsequent question: what are the parameters that govern this process which generates the data, right? So to recall the live session, we had discussed this point. So you kind of, in clustering and representation learning, you start with what is given and you try to extract some patterns out of it. Either they could be clusters or they could be important directions. Whereas in estimation, what you try to do is you go back to the past and you look at the whole process that generated the data, right? So, and then you try to model that. So you go back to the source from which it all came. Okay, so so this is what professor calls these things generative stories, right? So you have a coin within a box, and then you flip the coin or you press a button, and out comes a number which is 1 or 0, right? So you have a sequence of ones and zeros, and what you need to do is you need to model the distribution that is generating this data. And in our case, this one obvious distribution is the Bernoulli, right? So Bernoulli with parameter p, and this p always corresponds to the probability of x being 1. Okay, so for the assignments as well as for the exam, p will always stand for p of x equal to 1. Okay, so that is the parameter, the number of heads or the number of ones. Okay, that is Bernoulli of p, and we say that x is sampled from Bernoulli with parameter p. Okay, so the other distribution that we have seen is Gaussian, and see these are all continuous data in some sense. Earlier we had more or less discrete ones. So this is just a Gaussian distribution with 2 parameters, mu sigma square, right? All this you already know. What's the point here? Once we have the observations, we then come up with a model to explain these observations. These models have some parameters, right? So you have data, you have a model, and then you have parameters for the model. Your goal is to estimate the parameters using the data. Okay, so the 2 main methods are MLE and Bayesian estimation or Bayesian modeling. So first we'll very quickly look at MLE. So MLE depends on 2 things, right? One is of course the data, the other thing is the model, right? So the maximum likelihood estimate will depend on what kind of model you choose. So the most important thing is the likelihood function, right? So you have some data which is parameterized. This distribution is parameterized by some theta, right? So theta could be p in the case of Bernoulli, or mu sigma square in the case of Gaussian, right? So, or in the case of GMMs, it could be a whole host of things like mu sigma square, pi k, all that, right? So theta generally stands for the parameter governing the distribution, and d is the data set. So that is the likelihood. 2 important assumptions we already know: this independence and identical distribution, right? IID assumptions. So this matters because if you notice these, there is a sequence, right? So we have given this as a sequence, but actually the ordering doesn't matter. Okay, so the order in which you present these items doesn't matter. It's a set. Rather, I think it's better to call it a set rather than a sequence. So the observations are independent and they're also identically distributed, meaning the distribution governing each xi is the same. So the same coin is being tossed, or so whatever mechanism that generates the data is the same, right? So that is a very crucial assumption which will stick with us for all the weeks, right? Remaining weeks also. So if you do MLE for Bernoulli, it's like pretty straightforward. If you have a data like this, you have 3 ones and 2 zeros, right? So likelihood will be p cube into 1 minus p square. So the independence again comes here because they're all 5 observations are independent. You can just multiply them, and the identical distribution comes here because of the p, right? Had they been differently distributed, you would not have used p for all of them. Okay, so the next step is to compute the log likelihood, just 3 log p, 2 log 1 minus p. Okay, differentiate it with respect to p and set it to 0. Okay, and you end up with the maximum likelihood estimate for p to be 3 by 5. So what is this? This is nothing but the mean of your observations, right? So it turns out that the MLE for the Bernoulli distribution has an very intuitive representation. It is the mean of the observations. I think there is some noise from somewhere. Is it from? Okay, yeah. So that is MLE. MLE for Gaussian is in same way. Only thing is that instead of a product of probabilities, there are a product of densities. Okay, so you have a PDF here, probability density function, not a PMF, right? So you multiply all these densities together, and same process, take the log, differentiate it with respect to mu, set it to 0, right? And you'll end up with the same form for the MLE, right? So it's again the mean of your data points. Okay, so that is MLE. I think there's nothing very challenging here. You have already done this in stats 2. Okay, so when we come to Bayesian modeling, so why do we need to look at Bayesian modeling? The reason we start doing this is because we might be having some hunch or idea about the parameters of our model, right? So if I take the coin example, I might know that the coin is kind of heavily biased towards heads, right? So if I know that information, then that is going to, can I use that information to better model the system? Okay, so the prior is actually something that gives us an idea of or something that encapsulates what we think about our parameter P even before seeing the data. That is why it's called the prior. Okay, so prior is prior to seeing the data, and then what happens is you see the data. So the data could, the whole point of having data is it could modify your beliefs, right? So data could modify the prior, and how it modifies your prior belief is through the likelihood. Okay, and evidence is something that is thrown in for normalizing the whole thing. So the prior is modified by the data through the likelihood to result in the posterior, right? So it results in the posterior. So it's called Bayesian modeling because you have this Bayesian update rule coming in. Posterior is likelihood times prior by the evidence. Okay, so the evidence is just a normalizing constant, as you all know. If we put symbols to all this, you notice that the prior is P of theta, right? So note that this does not have any D associated with it. Comes even before you see the data set. It's not dependent on the data set. And then you observe the data set, and that is your likelihood. And if you take the product and divide it by the evidence, you get your posterior, right? So posterior is updated belief, meaning what happens to your understanding of theta after you see the data set. That is why it is P of theta given D. Okay, so this is the basics of Bayesian modeling. So in our course, it's very simple. We only look at Bernoulli, and the prior for the parameter P is beta, the beta distribution. So beta distribution has two parameters, alpha, beta, and it takes this functional form. So Z is Z, or Z is nothing but this normalizing factor, right? So it has to represent a probability distribution, right? So you integrate from 0 to 1. So this whole thing should sum to 1, right? So Z is thrown in for that. So what is this beta? Beta is actually called the conjugate prior of the Bernoulli, right? So why is this important? So let's just go back. So prior is of the form p power alpha minus 1 into 1 minus p power beta minus 1, and for Bernoulli the likelihood is also of this form, right? So p power number of ones and 1 minus p to the power number of zeros, right? So if you choose this kind of a prior, the beta prior, then it's very easy to compute the posterior, right? So posterior also takes the form of a beta distribution. So what is the form it takes? You have n1 zeros, n1 ones, and n0 zeros. Can someone tell me what will be the, okay, prior is this. This is the prior. What will be the posterior?
Alpha plus n1 and beta plus n0.
Right. So it is as simple as that. So this is the posterior. So what this is essentially saying is that I have some prior belief about my parameters. This updated belief is also going to look like some beta distribution if the prior is beta, right? So that's what this is saying. Now from here, so what your Bayesian modeling gives you is a distribution over the parameter, right? It's in MLE you got a single value. So in Bayesian modeling you are going to get a distribution of over the parameter. Okay, so from this there are two parts. So how do you get one value like what you had in MLE? There are two parts. One is called the maximum a posteriori estimate, right? So we didn't discuss much about this. but this is nothing but the mode of the posterior, right? So you have the posterior, find that value of p where it becomes maximum, right? So which can be simply differentiating the posterior with respect to p, setting it to 0, right? So typical estimate, point estimate. The other way is the expected value. Okay, so expected value for this setup is nothing but alpha by alpha plus beta. Okay, so did you all get what we mean by point estimates in this context? Any questions?
Could you explain this MAP estimator?
Okay, so MAP, what it's doing is
Is it posterior expected value?
On the expected value of the posterior, that is the second one. The MAP estimate is the mode. Mode is like where does your distribution peak?
Okay.
Okay, so for a continuous case, that is what it is. So where does the density peak? So that will give you 1 point, right? 1 point on the x-axis, on the p-axis, where the curve will reach its maximum. That is taken as the estimate.
Okay, thank you.
Okay, so that's the simple part of week 4. The slightly more complex part is GMMs, right? So we go for Gaussian mixtures because Bernoulli and Gaussian, the normal Gaussians are too simple, right? So we'll not get such simple cases in real life data sets. So we need to model more complex situations. And data sets are not going to be unimodal like the Gaussian, right? They are going to have multiple modes. So you need multiple modes as in something like this, right? So this has 3 modes. So how do we model all this? You use something called latent variable models, right? And the Gaussian mixture model is one such instance. So there's a very simple generative story here. Instead of having a coin inside a box, you have k mixtures sitting inside a box, right? You first pick a mixture and then you sample a point from the mixture, right? So in general, these are called mixture models. Now, since we are dealing with Gaussians, they are Gaussian mixture models, right? So there could be other mixtures as well. Okay, so this is the setup. We have k mixtures, pi 1 to pi capital K, and the means of the mixtures are mu1 to mu capital K, and these are their variances. Okay, so you have total 3k parameters for your model. Okay, so there are 3 into capital K number of parameters.
Sorry to interrupt you. Are you recording the session? It's not showing in the YouTube.
Yeah, we are. I mean, we are not streaming it, we are recording it.
Okay, you will stream it later?
We will share the recording and then later we'll upload it to YouTube.
Okay, thank you. Because now MLF session is there, I want to join, that's what.
Yeah, please go on. Yeah, this will share.
I can watch it later, right?
Yeah.
Thank you.
MLF, they are only discussing the mock paper.
Okay.
Yeah, right, we'll continue, right? So there are 3k parameters. Now, how many free parameters are there? I hope you all know that. How many free parameters are there?
3k minus 1.
Right, 3k minus 1. Why is that?
One less will be required to assess, find all the.
Correct.
5k is no
plus
need.
5k is 1.
Okay.
So.
Okay, right. So that sum is 1, right? So the value of the following expression is 1. So because of that, you can afford to get rid of one parameter, right? So there are 3k parameters in total. There are 3k minus 1 free parameters, right? So that is your GM. Okay, so that is the setup for the GMM. See, the generative process works like this. So just like what you saw in this k-means plus, right? So here also there is one set of probabilities, mixtures with some probabilities, and you have to sample one of these k mixtures, right, with this probability, right? And higher the probability, greater the likelihood of that mixture coming up, but it doesn't rule out the possibility of other mixtures being chosen. Okay, so you sample a data point xi. Let's call, sorry, you sample a mixture index. Okay, and we call that k. Let's say the kth mixture was selected, and this is what is called the latent variable, right? So this zi is called a latent variable because it is latent or hidden. Okay, so actually it is not there. At least on the surface, we don't see it. We only have certain number of mixtures and their parameters, right? This is something that we introduce or which is latent or hidden, right? Not visible. And we use this in our modeling process. Okay, so the for every data point xi, there's going to be some latent variable zi, which denotes the mixture from which that point has come, right? So zi is equal to k. And now you sample a point from this kth Gaussian. Okay, so this is the generative process. Now, why is this generative process? Where will this help us? This will help us in coming up with the density of the GMM, right? So the density of the GMM is what? So can someone tell me how I have written this thing down? Where does this formula come from?
It is basically probability of choosing a kth mixture.
That is correct. Okay.
Multiplied by, I mean, the product with the density of the Gaussian density of the kth mixture.
Okay, that is correct. Right. Yeah. So the point x whose density we are interested in could have come from any one of the capital K clusters mixtures, right? So these are exclusive events, right? These are mutually exclusive events. If it came from mixture 1, then you can roll out the other k minus 1, right? So you have to treat each of them as a set of k mutually exclusive events. So by the law of total probability, what you can do is you can sum up all these probabilities. So first one is the probability that it came from cluster or mixture k. Given that it came from mixture k, what is the density of that Gaussian, right? So that is the density of the GMM as a whole. Okay, so this, if you want to remember this, think about the generative process. Sample a mixture index, that is the first part, and then sample a point from that Gaussian. That is the second part. You multiply them, then sum it over all k mixtures. So that's the density. Okay, so once you have the density, what you can then do is whatever you did before for Bernoulli and Gaussian, you can do MLE for a GM. Only thing is that it's going to be much more complicated, but the principle remains the same. Right? So you have a set of parameters. You want to use data to estimate the parameters. Okay, so plug in the data and use the IID assumption. So that is what this is. So log likelihood then will be sum of all these things. Okay, now I have just replaced FGMM of xi with whatever we had in the earlier slide, right? So far so good, but this is where we get stuck. We have a logarithm of sums, right? And we can't proceed further at this stage without some kind of mathematical machinery, right? And that mathematical machinery is called the Jensen's inequality, right? We don't need to get too much into all this. So it's just enough if you know that we can use this inequality for concave functions, right? Log is a concave function, and you can just use this to get hold of this expression here, right? So what we have done is we have converted log of sums into sum of logs. Okay, so that is what we have done using the Jensen's inequality. The price we pay is the change of equality to inequality, right? That is the cost that we pay. So we can no longer work with the original likelihood. We are forced to work with this modified log likelihood. Okay, any questions here? This can be a bit tense. Any questions? Okay. So this log likelihood, this modified log likelihood is what for the likelihood? Is it a lower bound or upper bound? This quantity?
Lower bound.
Lower.
Lower bound.
Okay. Right. So if you push the lower, if you try to maximize the lower bound, why would that help? So yeah, I can't maximize this, but why do you think maximizing this will help me in any way? Any thoughts? Okay, so you have a quantity, this quantity is greater than something, right? So if I try to increase this quantity, okay, then I am kind of indirectly increasing this, right? I don't have a direct hold on the log likelihood, but at least I have a hold on something that is greater than or equal to. So if I maximize this, I am kind of indirectly maximizing this. Okay, so here all complete detail. So this is over the data points, right? So this summation comes from the original log likelihood. This inner summation, right? It comes from the Jensen's inequality, right? By moving the log of sums into sum of logs, right? So that is where this comes from. And these lambda ik's, they all are fractions, right? They all lie between 0 and 1. And for each data point, they should sum to 1. Okay, so if you have, let's say, 10 data points and 3 mixtures, how many such lambda values will you have?
30.
Okay, right. So I think that is clear. Okay, so the final part is estimating the parameters for the GMM. You have what is called the expectation maximization algorithm for this. So you initialize theta naught. Theta naught is those 3k parameters, right? So all those 3k parameters put together, we are calling it theta. So what are we going to do? We are going to initialize all of them using Lloyd's. So with capital K clusters, right? So I hope you kind of get an idea of what's happening there. See, once you cluster them with Lloyd's, you will get hold of K means, right? K mu's, mu1 to mu k. So using mu1 to mu k, what can you do? How can you get pi k from that?
Pi k is the ratio of data points in each cluster.
Right, that is correct, right? So pi k is the number of points, ratio of points in that kth cluster divided by total number of points, right? So that ratio is pi k. Mu k you already have. How about sigma k square? What is the variance of the kth mixture? Initial value. It is just the variance of that cluster, right? So that is the variance, theta naught value that you have. Okay, so pi k, mu k, and sigma k square will be the ratio of points in kth cluster, mean of the kth cluster, and the variance of the kth cluster. Okay, so that is what you have. And then until convergence, what you do is you do one E step and then you do one M step. So what are these two? These are just ways to estimate lambdas and thetas. So first you estimate lambda using the theta t that you already have, and then you use the lambda that you just got to get the next step of theta. Okay, so main thing that you need to know is what do these terms mean? What do lambdas mean? So lambda ik has a very simple interpretation, which is given a point xi, what is the probability that it belongs to mixture k? Okay, so it's a simple conditional probability of point z point I belonging to cluster K, mixture K, given that point. Okay, so we have simply used the base rule here. I think this should be clear. If not, just let me know.
Sir, in the denominator, the probability for xi should be for all clusters, isn't it?
Yeah, for all clusters.
So, but there was one question where I think it was in the graded where only the first two clusters was taken into consideration.
I think there were only
Sir,
two
there were three
mixtures in that
mixtures,
problem, right?
and the point was -3. Taking three clusters, the answer was not 0. It was coming around 0.22.
Which question is this? Which question is this? I need to.
Sir,
Can you tell me the
let me
question
just
again?
check it and come back to you.
Okay, yeah. Okay, so that is lambda ik, and the m step is also likewise simple. So once you have the lambda ik's, the theta values, right? Sorry, the mu sigma square pi k values are nothing but the weighted mean, weighted variance, and this is not weighted anything. This is just the probability of choosing the k mixture, right? So I hope you get the m step. Mu k sigma k square is quite simple to remember. This also you should, try to get it. So what this is saying is that look at every point in the data set. What is the probability that it belongs to mixture K? Sum all these probabilities divided by n. Okay, so that's what this is saying. Final. Yeah.
So in previous slide, I have one confusion.
Yeah, which one?
Is lambda k summation, isn't it 1?
Lambda k, this one, this denominator.
Yeah.
This is not 1 for when you sum from I equal to 1 to n, this is not 1, right? So see, for each point, you have k, capital K such lambdas. They all sum to 1.
For each point.
So for each point, so what I'm saying is, let's take this. So lambda, assume that there are 3 for point 1. Okay, we just lambda 1 plus lambda 1 2. There are 3 mixtures. This is 1, right? Because what is the probability that this point came from mixture 1, mixture 2, mixture 3? If I add all these 3 together, it has to be 1.
Right.
Okay, what is not 1 is this need not be 1, because what this is saying is, what is the probability that first point came from mixture 1, second point came from mixture 1, third point came from mixture 1. It could be, say, this could be 0.5, this could be 0.4, this could be 0.5 again, right? So it can exceed 1, it can be below 1. We don't know. All that we can say is, what is the sum of probabilities of a given point coming from all k mixtures, that sum is going to be 1. Okay. So that is what yeah.
Sir, that was question number 8 of practice assignment.
Question number 8 of the assignment. 1 second. So question number 8. So what you are saying is that there were 3 mixtures there, right?
Yes, sir.
So.
But it is mentioned, na? This is coming from mixture 2. So that is why.
No, that's not mentioned. No, that's not the question. The question is something else. This is following Bayes theorem. So
No.
the probability.
Which question is that in graded assignment 4?
Practice assignment, question 8. So if you go through the solution, no, I don't think solution is given. Proper solution was not given actually.
It should see we point
Yes,
is the
sir.
answer,
So
right?
the thing is, it doesn't matter whether the point is very far from a cluster. Still, it does have some, at least even if tiniest, it does have a little bit of probability. It's never zero.
No, that is correct. You should add all three clusters. I think it should. I think we would have added. If
Sir, if
the
I
solution.
was taking only cluster 1 and cluster 2, I was coming to this 0.22. But taking the third cluster also, the answer was not 0.22.
Okay, I'll check that. But by now, we see someone would have pointed it out in discourse. I think so far, if no one has pointed it out, I don't think the answer will be wrong. But anyway, I'll check and get back. Can you create one thread in discourse so that?
Okay, sir. Okay, sir.
Yeah. Okay. So end step. Any doubts? Anyone? Okay. So once end step is done, final thing is hard clustering, right? So just like you have in k-means, you here you have what are called as soft clusters. Now, one way of generating hard clusters is doing this, right? So I'll just quickly show you one example and then we'll close that part. Okay, so
sorry, what question she was asking? PA question number 8.
Yeah.
Yeah, I took 3 also. I took 3 components. The answer was correct only.
Okay.
Maybe some calculation mistakes.
Yeah, possible. Okay, so hard clustering very quickly. So see, if you have 6 data points and you have 3 mixtures, then your lambda could look something like this, right? So it is a 6 cross 3 matrix. So 6 data points, each row corresponds to one data point. This is the probability that the first point belongs to mixture 1. This is the probability that the first point belongs to mixture 2 and first point belongs to mixture 3. If you sum all these values, you should get 1 for each row. Right? Now, what we are saying is we can assign a cluster or a mixture to each of these points. So for the first point, since the second mixture has the maximum probability, I'll assign the index of 2 to this point. Okay. Likewise, for the second point, since the third mixture has maximum probability, I will assign this as the value. Right? What will I do for point 3? What will be the index? 1.
1.
Right? 1. And then
3.
3.
3.
2. Right? So this is what is hard clustering, right? This is these are soft clusters. Why are they soft? Because for the first point, or for any point for the matter, I'm not explicitly saying that it should belong to cluster 2. All that I'm saying is that there's a higher chance that it belongs to cluster 2. Okay, so it is soft. The moment you make a hard decision and say no, it has to come from cluster 2 and not any other cluster, you are making a hard choice. Okay, so that is what is called hard clustering. Okay, so that ends week 4. Any questions on week 4? I just want to discuss one thing with respect to week 1, which I said I will do regarding this covariance matrix. But for that week 4, any questions? Okay. So I just very quickly go over this point in week 1, which there was a problem.
Actually, I do have a doubt here how PC components are arranged. PC1, PC2 till PCK.
Okay, so.
And how to get that K?
Yeah, that K, that heuristic is there, right? Lambda 1 by, so sum of lambdas divided by total sum of all lambdas.
So algorithm will decide after calculating the lambda ones and these eigenvectors, everything.
Yeah, only in the end. So see, actually this, for the purpose of explanation, what Sarah has done is he has given these rounds, but
could you please brief the steps just briefly what algorithm does?
Algorithm does only one thing, right? So see, there are multiple. It appears as though there are many steps, but okay. So if you want to go
No, I'm
step,
clear till the calculation of eigenvalues and eigenvectors. After that, I'm unable to understand how these are arranged and how K is decided.
see, once you get eigenvalues and eigenvectors, you are going to get lambda 1, lambda 2, so on, right? So this is how they'll be arranged.
This
All the
will,
way up.
no, I will get in this order or this will be arranged.
You will. So if you think about a computational routine that does this for you, it will give you in this order.
So for one round, only one lambda will be taken, right?
Yeah. So see, that's what I said, right? So Sar has given this round. He has explained it in this fashion because it's easier to understand. But in practice, what happens is that you get all these d values in one go.
Actually, in first round, I will get the covariance matrix and I may get 2, 3 lambdas, right?
No, you will get only one lambda. You will get the largest lambda.
Yeah, I will get to maybe 2 or more lambdas, but I will take the largest lambda.
That's what I said, right? So see, we don't. It's only for the understanding purpose that we have given these rounds. Okay, so moment you get the bigger picture that these d values are the d eigenvalues, you can do it in one shot, right?
Okay.
So you can do it in one shot. Okay,
so there is no round 1, round 2, round 3, no, nothing like that.
It is in for understanding it. It's good to understand it that way because you know step by step he kind of leads you to why we are doing this, right? So you first do main direction, then you do residues, then you do residue of residues. So that's good for understanding, but in practice you get these d values in one shot.
Okay, from the covariance matrix I will get d lambdas.
D lambdas, yeah.
And I will the algorithm will arrange it in the decreasing order.
Yeah, it will either increasing or decreasing, but what we need is the decreasing order.
Okay, algorithm will arrange.
It will give you, yeah. So if you look at a typical computation, like if you look at a library like NumPy, if you plug the covariance matrix, NumPy will give you the d values which are sorted in ascending order.
Okay. And corresponding eigenvectors will be calculated.
That also will be given. But
so
of course,
this PC1 is nothing but eigenvector or something else calculation will be there for PC1?
PC1 is nothing but the first W1 corresponding to lambda 1.
Okay. So in this from lambda 1 to lambda d, again that 95% will be calculated and the K will be taken.
And then, yeah, you will choose that K which explains 95% of that variance.
Okay, then. Thank you, clear.
Okay, so there's one point very quickly.
So if K, I mean sum of K is 94.99 and sum of K plus 1 is 95.01, then we should take K plus 1 only. If we have to choose
you
a
have to
particular
cross.
K.
You have to cross, or you should at least be.
I mean, there could be a question in which we have to find out the K, which explains 95% of variations.
Yeah, I mean, if your K, if that comes out to be 94.99, you should not take that. You should take the next.
Okay.
Okay. So yeah. So
and this sum of K lambdas is projected variance, right? Lambda 1 plus lambda 2 till lambda K.
What is projected variance? I know it's some MLF term you are using.
Yes. That's what I'm asking. The top one in the 95% we derived, we have top K values and denominator as total variance, right?
Yeah. Denominator will be total variance. The top K will be projected. Okay. So yeah, if I am not wrong, projected along the top K directions. Yeah. So those K, some of those K values.
This total variance, when you explained, I confused with those terms. That's what I need to clear it. Thank you.
Yeah. Okay. So there is one confusion that we had early on, which I will very quickly solve that. I mean, not solve. I mean, just go through that. So if you have a covariance matrix like this for a two-dimensional data set, okay. Now here is the question: what are x1, x? So can someone tell me what x1 is? What is the vector x1?
Okay.
So if I were to write x1 as a vector, how will it look?
1 0
1 0, right? That's good. X2 is what?
0 1.
0 1, right? So we'll first stick to that. W1, W2, we can give some values. So this is the covariance matrix, and we had some confusion regarding the diagonal elements, right? So whether they are variance, whether they are the eigenvalues. Okay, so first question is, what is the variance along x1? Or how will you
4.
calculate it?
4 is the variance.
Okay, 4 is correct. Okay, now for a general direction W, what is the variance along that direction? What is the formula that we use?
W transpose CW.
Okay, good. So now if we use that for this x1 direction, what should it be? Use that formula for
2.
this. Variance is 4, correct? But
4 2.
no. So what I'm asking is, you told W transpose CW, that is correct. Now, how will I use that formula for x1 direction? Variance along x1.
X1 transpose C.
Correct.
X1.
Right? So that is what I want you to know. So x1 transpose CX1 is 1 0 into the C into 1 0, which is 4. Okay, so 4 is C11, first diagonal element. So the first diagonal element is not the eigenvalue. Okay, so first diagonal element of the covariance matrix is the variance along x1. Second diagonal element is what?
7.
Variance along 2.
It's a variance along x2. Okay, so please don't confuse the diagonal elements of C with the eigenvalues. Now this part is clear, right? So the diagonal elements give you the variance along the standard basis, which is x1 and x2. Now how will you compute, let's say W1 is 1 by root 2, 1 by root 2, right? It's the 45-degree line. So what will be variance along the first principal component? What is variance along W1?
That will be the eigenvalue of.
That is correct, right? So that will be lambda 1, but you can also compute it like this. Okay, so the same formula, the formula is the same. Only thing is that you use different vectors in different places. And this is what is lambda 1, right? So this is lambda 1. Okay, so see, this turns out to be, say, 7.5. I mean, this is not actual lambda 1. I may be wrong with my W1, but if you assume that these calculations are true, this thing is lambda 1. Okay, this 7.5 is not the diagonal element of your covariance matrix. Please make that note. Okay, so
You mean to say eigenvalues and variance are different for this matrix?
No. So what I mean to say is the eigenvalues are the variances along the principal component. So I just write it down. What I'm saying is the eigenvalues, this is the first point that I'm saying. The eigenvalues are the variances along the principal components. Okay, this is point number 1. Point number 2 is eigenvalues need not lie on the. Okay, so this was the confusion earlier. Eigenvalues need not be on the diagonal of the covariance matrix. Okay, are you clear about these two things?
Yes.
Eigenvalues are still variances, but along principal components.
So 7 is the variance along W1.
No. 7 is the variance along x2.
7.5, sorry.
7.5, yeah. 7.5 is the variance along x1. Along W1.
W1, yeah.
Likewise, whatever you do along W2, that will be the lambda 2. Okay, but this 4 and 7 are variances along x1 and x2. Okay, I hope that is clear. Yeah. Okay, so one final question before we end the session. So if I use W1 and W2 as a basis, what will be the covariance matrix in this basis? How will it look like?
Sir, this is a diagonal matrix containing the lambda value.
Correct, right? So that is correct. So this is now I hope you understand what the link to diagonalization, right? You had this matrix C to begin with. If you move to this new basis consisting of the eigenvectors W1 and W2, in that basis your your covariance matrix will be diagonal, and there the diagonal elements will be not just the eigenvalues, but they'll also be variances along those two directions, right? So think about it this way: instead of using x1, x2, I'm using w1, w2 to describe my data points. All right, so I think that's all we had.
Sir, just along with this thing, can you please add in the material, sir?
Which one?
That's right now that what you have did in this.
This covariance matrix thing.
Yes,
No,
if
no,
you can
these
add
slides, the
along with the
presentation
slides.
slides.
Okay, so along with that, it will be tough. I'll share it separately as a PDF.
Okay.
When it will be available?
So slides we have already shared for week 1, week 2, week 3 also we'll share. Along with that, by tonight we'll share.
Any mock test paper you're planning to release?
Sir, week 3 is not shared, sir.
Week 3 we'll share, so yeah. Okay, then I think.
Mock
no
test
mock?
you're not giving?
No mock. See, mock will be similar to assignments. So it will be like not of great help.
Actually, no previous question papers, nothing. So we are a little bit worried about test.
So it will be not be too hard. So you can, if your basics are clear, then
I think we need more sums to practice, I think, because all theory is mentioned, but applying that is something which is.
Yeah, how many questions we can expect?
Since I am not sure. Not sure if I am supposed to reveal that. Nitin, Anamika, we are not supposed to reveal that, right? Yeah, I mean, you can do it in.
MLF, they said that it will be something between 16 to 20.
You can expect a similar number.
Will it be solvable in 1 hour? That is the main concern.
I think, yeah, yes. Okay, I think that is all we had. Shall we close?
Thank you,
Any tips for quiz preparation?
I think you have to focus on the concepts more than
Calculations?
calculations. Don't worry too much because I think we haven't like tested you on that part too much. I mean, we won't be testing you too much on whether you can take square roots properly or all that. So
Yeah, that's what in this normal distribution, that calculation always I'll do some mistakes.
yeah, hopefully you will.
Okay, thank you.
Yeah, thanks.
And sir, we are supposed to remember all equations.
Yeah, most of them. I think so those you can derive, you don't need to, but other than that, you need to.
Okay.
So this PDF and week 3, kindly share, sir, if possible by today night.
Yeah.
Okay. Thank you.
Thank you everyone.